Have you ever wondered what happens when a planet gets too close to its star? Somewhere in the depths of space, there's a world called WASP-12b, a gas giant so near its sun that it's being ripped apart, piece by piece. It's hotter than fire, darker than night, and locked in a death spiral that's sealing its fate with every orbit. Astronomers call it the death planet, a place where the laws of physics bend under unimaginable heat and gravity. And what's happening there has left scientists both fascinated and deeply unsettled. The birth of the WASP project. For most of human history, we looked up at the night sky and wondered if the tiny points of light, those faraway stars, might have worlds of their own. For centuries, it was pure imagination. The idea of other Earths orbiting other suns was a philosophical debate, not a scientific one. We had no way to see beyond our solar system, no instrument sensitive enough to detect the subtle gravitational whispers or faint shadows cast by unseen worlds. But that all changed in the late 20th century. In 1995, two Swiss astronomers, Michel Mayer and Didier Queloz, announced something that would change astronomy forever. Using a technique called the radial velocity method, they detected the first confirmed planet outside our solar system, 51 Pegasi b. It was a giant gaseous world orbiting a star similar to our Sun, about 50 light-years away. This discovery shattered old assumptions. For one, the planet's orbit was extremely close to its star, far closer than Mercury is to the Sun. This was completely unexpected. Theoretical models at the time predicted that gas giants could only form in the cold outer reaches of a solar system like Jupiter or Saturn. Yet here was a hot Jupiter, skimming the surface of its Sun every few days. 51 Pegasi b opened the floodgates. Over the next decade, astronomers around the world began scanning the skies for similar signatures, tiny tugs and dimmings in starlight that could reveal more hidden planets. What they found was staggering. Dozens, then hundreds of worlds, each stranger than the last. Some orbited twin suns, some were frozen gas giants drifting through interstellar space. Others were boiling infernos with winds that could shred steel. By the early 2000s, the hunt for exoplanets had become one of the fastest growing fields in astronomy. New telescopes, both on the ground and in orbit, were being designed specifically for the task. And among the most ambitious of these efforts was a project known as WASP, the Wide-Angle Search for Planets. In the early 2000s, exoplanet detection was still a painstaking process. Instruments like HARPS in Chile and Keck Observatory in Hawaii were powerful but limited to studying one star at a time. What the WASP team proposed was radically different. A wide-angle survey that could monitor tens of thousands of stars simultaneously, searching for the telltale dip in brightness that occurs when a planet passes in front of its star. This was called the transit method, and it would become the workhorse of modern exoplanet hunting. The idea was elegant. As a planet crosses or transits the face of its star from our point of view, it blocks a tiny fraction of the starlight. That dimming, sometimes less than 1%, repeats at regular intervals, revealing not only the presence of a planet, but also its size and orbital period. The WASP project built two robotic observatories, one in the Canary Islands, SuperWASP North, and another in South Africa, SuperWASP South. Each observatory used an array of wide-field cameras pointed at huge swaths of the sky. Every few minutes, they snapped images of thousands of stars, recording subtle fluctuations in brightness. Over time, algorithms combed through the data, flagging any star that showed a consistent pattern of dimming. It was, in essence, a celestial lottery. Countless stars watched night after night, waiting for one of them to blink at just the right rhythm. And in April 2008, one of those stars did. The star was catalogued as WASP-12, a sun-like star located roughly 1,400 light-years away in the constellation Auriga. Nothing about it seemed extraordinary at first glance. But when the data came in, the WASP team noticed something strange. A faint, rhythmic dip in its light, repeating every 1.09 days. That meant whatever was orbiting WASP-12 was completing a full orbit, a year in its own sense, every 26 hours. To put that in perspective, Mercury, the closest planet to our Sun, takes 88 days to complete a single orbit. This world was moving 80 times faster. At first, the astronomers thought it must be an error, perhaps a data glitch or instrumental noise. No planet could survive that close to its star, they reasoned. The heat would be unimaginable, and the gravitational forces immense. Yet the pattern repeated with eerie precision, night after night. The dip was consistent, the signal unmistakable. What they had found was real. They called it WASP-12b, the first confirmed planet from the Super-WASP survey, and from the start, it defied everything scientists thought they knew about planetary survival. When the team ran the numbers, they realized how extreme this world truly was. WASP-12b was a gas giant, roughly 1.4 times the mass of Jupiter, but nearly twice its size, bloated and stretched by the relentless heat of its star. Astronomers would later discover that the planet's atmosphere is being siphoned off, forming a giant ring of gas around the star, a process that will eventually lead to the planet's destruction. But in 2008, that was still years away. At the time, the discovery of a massive gas giant orbiting that close to its sun was shocking enough. The initial reaction among scientists was disbelief. Some thought the data had to be wrong. Others suggested it might be a binary star system or some kind of optical illusion. But follow-up observations confirmed it. The planet was real, and it was on a death spiral. At first, they thought it was a mistake, but the more they looked, the stranger it got. In the years that followed, astronomers turned some of the world's most powerful telescopes toward WASP-12b. They wanted to understand how such a planet could even exist. Then, in May 2010, the Hubble Space Telescope made a strange discovery that shocked the scientific community. Using ultraviolet observations, Hubble detected a faint halo of gas around WASP-12, evidence that the planet was literally leaking its atmosphere into space. Streams of hydrogen and helium were being pulled from the planet's surface and swallowed by the star. It was the first time astronomers had ever witnessed a planet being consumed by its sun in real time. Scientists had long suspected that such events happened, that stars could, under the right conditions, devour their planets. But this was the first direct observation. For the first time, humanity had caught the universe in the act of planetary death. What they found was both horrifying and mesmerizing. WASP-12b wasn't just orbiting its star, it was spiraling inward, inch by inch, closer to total annihilation. Calculations showed that the planet's orbit was decaying, a phenomenon never before measured so precisely. Over time, it would continue to lose energy and fall toward its star, much like a satellite losing altitude and burning up in a planet's atmosphere. Astronomers estimated that WASP-12b had between 3 and 10 million years left before it would be completely destroyed. In cosmic terms, that's an eye blink. This made WASP-12b one of the first planets ever observed in its final stages of life. By the time the data was fully analyzed, it was clear that WASP-12b wasn't just another hot Jupiter. It was something far more extreme, an ultra-hot Jupiter, existing in conditions previously thought impossible. Its orbit was so close that it was tidally locked, meaning one side of the planet always faced its star, while the other remained in perpetual darkness. On the day side, the temperature soared high enough to vaporize iron and titanium. On the night side, gases condensed and flowed back toward the blazing hemisphere in violent winds moving thousands of miles per hour. Scientists estimated that the planet's upper atmosphere was expanding, forming a comet-like tail of vaporized material trailing behind it. In ultraviolet light, the system glowed faintly as gases escaped and spiraled toward the star. The more they studied WASP-12b, the clearer it became that this was not just a new planet. It was a new kind of planet, one that forced astronomers to rethink their models of how worlds form, evolve, and die. Before WASP-12b, the term hot Jupiter already pushed the limits of what astronomers expected to find. But this planet went further. It blurred the line between a planet and a star's doomed satellite. How could such a massive world form so far out, then migrate inward without being destroyed in the process? What kind of physics could keep it intact long enough for us to observe it? These questions reshaped the study of exoplanets. Suddenly, astronomers realized that planetary systems could be far more dynamic and violent than our own. In our solar system, planets move on stable, nearly circular orbits, but around other stars, chaos reigns. Planets can migrate inward, collide, or be ejected entirely. Some are born close to their stars, others drift inward over millions of years. WASP-12b seemed to be caught in the final act of this cosmic dance, a planet that had wandered too close and was paying the ultimate price. By the late 2010s, WASP-12b had become one of the most studied exoplanets in the galaxy. Its name appeared in countless scientific papers, its image rendered in hundreds of stunning visualizations. But despite all the data, one thing remained true. It still didn't make sense. A planet that dark, that hot, that close, and that doomed shouldn't exist for long enough to be observed. Yet there it was. As astronomers continued to monitor the planet's orbit, they began to notice subtle changes. Its orbital period was shrinking, its path decaying faster than predicted. Each passing year brought it a tiny bit closer to destruction. In a way, WASP-12b had become a window into the future, a glimpse of what happens when the delicate balance between a planet and its star is broken. It was a scientific discovery, yes, but it was also something deeply human. Because in that dying world, melting and unraveling under the glare of its sun, astronomers saw a reflection of our own planet's distant fate. One day, billions of years from now, our sun could expand into a red giant and consume the inner planets, Mercury, Venus, perhaps even Earth. A star's gravitational grip. To put that into perspective, Mercury, the innermost planet of our solar system, orbits at about 35 million miles from the Sun. That means WASP-12b sits 17 times closer to its star than Mercury is to ours. It's so close that the temperature on its surface is estimated to reach over 4,600 degrees Fahrenheit, 2,500 degrees Celsius. Hot enough to melt titanium, vaporize rock, and tear the very molecules of its atmosphere apart. Astronomers had seen hot Jupiters before, massive gas planets that orbit close to their stars, but this was something different. WASP-12b wasn't just a hot Jupiter, it was an ultra-hot Jupiter, a planet so close that its very orbit defied logic. And what made it even more terrifying, the planet wasn't stable, it was dying. To understand why WASP-12b's situation is so extreme, you first have to understand orbital mechanics, the cosmic dance between gravity and velocity that keeps planets in motion. In space, everything moves in balance. A planet wants to move in a straight line, but the gravity of its star constantly pulls it inward. The result is an orbit, a continuous fall around the star. Think of it like swinging a ball on a string. The faster the ball spins, the tighter you have to hold the string. If you let go, the ball flies off. If you pull too hard, the ball crashes into your hand. That's what's happening between WASP-12b and its star. The planet is moving so fast that it completes a full orbit, its entire year, in just over one Earth day. That means if you lived on WASP-12b, the sun would rise and set every 24 hours, and each of those days would mark an entire year of your planet's existence. But the balance between velocity and gravity on WASP-12b is pushed to the extreme. Its star's gravity is so strong, and the planet is so close, that the delicate equilibrium is breaking down. The planet isn't just orbiting anymore, it's spiraling inward, ever closer to destruction. Astronomers call it a decaying orbit, a phenomenon where a planet's orbit slowly tightens over time. Every rotation brings WASP-12b a little bit closer to its star. But why? Part of the answer lies in tidal forces, the same kind of forces that cause Earth's oceans to rise and fall. On Earth, the Moon's gravity tugs gently at our oceans, creating tides. On WASP-12b, however, the star's gravitational pull doesn't just raise tides, it stretches the planet itself, distorting it into an elongated, egg-like shape. The immense gravity difference between the side of the planet facing the star and the side facing away generates friction deep within the planet's core. That friction converts orbital energy into heat, and over millions of years, that process causes WASP-12b's orbit to slowly decay. In other words, the planet is falling. Scientists estimate that WASP-12b is moving closer to its star at a rate of roughly 10 to 15 milliseconds per year. That might not sound like much, but on a cosmic scale, it's a death sentence. Within 3 to 10 million years, the planet is expected to be completely torn apart or swallowed by its star. That may sound like a long time, but in the life of a star system, it's a blink. Mercury, the smallest and innermost planet in our solar system, experiences scorching temperatures and intense radiation from the sun. During the day, its surface can reach 800 degrees Fahrenheit, 430 degrees Celsius. That's enough to melt lead. But even Mercury, with its extreme environment, still has the luxury of space, a comfortable 35 million miles of it between itself and the sun. Now imagine moving that same planet 33 million miles closer. That's WASP-12b's reality. At just 2 million miles away, the difference in gravitational strength is astronomical. Gravity increases with the inverse square of distance. So, at that proximity, WASP-12b experiences a gravitational pull from its star that is hundreds of times stronger than what Mercury feels from the sun. The star's radiation doesn't just heat the planet, it boils it alive. The host star, WASP-12, is a yellow dwarf star roughly the same size as our Sun, but slightly hotter and more massive. It's located about 1,400 light-years from Earth in the constellation Auriga. When the Hubble Space Telescope turned its gaze toward the system in 2010, what it saw stunned scientists. Material streaming away from the planet, forming a glowing cloud of gas around the star. The planet wasn't just hot, it was disintegrating. The star's gravity was literally siphoning the planet's atmosphere away, pulling hydrogen and helium into a bright, donut-shaped ring surrounding the star. For the first time in history, astronomers were witnessing a planet being consumed by its star. The spectacle earned WASP-12b the nickname the Death Planet. For the astronomers studying it, the discovery was equal parts thrilling and horrifying. Here was a planet the size of Jupiter, one of the largest classes of planets in the universe, being shredded like tissue paper. Dr. Carol Haswell, one of the lead scientists on the observation team, described it vividly. WASP-12b is being devoured by its star. We are literally watching a planet in the process of being destroyed. In the cosmic scale of things, planets don't usually die like this. Stars die all the time, exploding as supernovae or collapsing into white dwarfs. But planets are passive survivors. They orbit, they endure. WASP-12b broke that expectation. It proved that planetary death wasn't just theoretical, it could be observed, measured, and predicted. The story of WASP-12b gets even stranger when you consider what life on such a planet would be like. If, of course, life could exist there at all. Because the planet is so close to its star, it's tidally locked, meaning one side always faces the star, while the other remains in eternal darkness. The same phenomenon occurs on our Moon, which always shows the same face to Earth. But on WASP-12b, the consequences are catastrophic. The day side is blasted by unrelenting radiation, reaching temperatures hot enough to vaporize metal. The night side, meanwhile, remains comparatively cooler, though cooler still means thousands of degrees. The result is a violent planet-wide storm system, as winds rip across the surface at up to 10,000 miles per hour, carrying vaporized atoms from day to night in a never-ending cyclone of fire and gas. It's a world where the sky glows with searing light, where the very atmosphere is being stripped away molecule by molecule, carried into the void. And through it all, gravity continues its slow, merciless pull. If WASP-12b were somehow transplanted into our solar system, it would orbit far within the orbit of Mercury, a place where no planet could ever survive. The Sun would rip it apart in days. Yet around its own star, it has managed to endure for what scientists estimate to be millions of years, albeit on borrowed time. Every orbit brings it closer to its end. Every revolution means more of its mass is stolen. Astronomers tracking the planet over the years have noted subtle changes in its transit timing, the tiny dips in starlight that occur when it passes in front of its star. Those changes confirm that its orbit is shrinking, tightening bit by bit. It's a slow-motion death that we can actually watch unfold across the vastness of space. The destruction of WASP-12b is a perfect laboratory for understanding how planetary systems evolve and die. For decades, scientists assumed that once planets formed, their orbits were relatively stable. But WASP-12b and other ultra-hot Jupiters have forced astronomers to rethink that assumption. Many now believe that these worlds may have once orbited much farther out, like Jupiter or Saturn, and were later pulled inward through gravitational interactions, either with their stars or with other planets. Over time, friction from the star's outer atmosphere and magnetic fields slowed them down, trapping them in these deadly close orbits. WASP-12b might be the final stage of that process, a once distant world dragged into a fatal embrace. And it's not alone. Astronomers have identified several other exoplanets showing similar signs of orbital decay, but none are as dramatic, as doomed, or as well observed as WASP-12b. Every planet tells a story, and WASP-12b's story is one of extremes: extreme heat, extreme gravity, and extreme proximity. Inside the Roche limit, there's a point in every gravitational relationship where things go too far, where attraction turns fatal. Astronomers call it the Roche limit, the invisible boundary where a planet or moon gets so close to a larger body that gravity begins to tear it apart. For most worlds, the Roche limit remains a theoretical threshold, something studied in physics classrooms or simulated through computer models. But for WASP-12b, it's not a theory, it's reality. This planet doesn't orbit near its Roche limit. It exists inside it, and that means it's dying. Slowly, violently, and spectacularly. To understand the Roche limit, one must first grasp what happens when two celestial bodies interact through gravity. Imagine a massive object like a star and a smaller one orbiting nearby. Both experience gravitational attraction, but not evenly. The side of the smaller object facing the massive body feels a stronger pull than the far side, a difference known as tidal force. On Earth, tidal forces from the Moon gently raise and lower our oceans, powerful enough to reshape coastlines, yet far from catastrophic. But on WASP-12b, tidal forces are magnified beyond comprehension. At only about 2 million miles from its parent star, the gravitational gradient across the planet is so extreme that it has stretched the gas giant into a distorted, elongated shape, an egg pulled thin under an invisible hand. The star's gravity pulls harder on one side than the other, literally pulling the planet apart molecule by molecule. The Roche limit defines the point at which a celestial body's self-gravity can no longer resist that stretching. Once a planet crosses that line, disintegration begins. WASP-12b has crossed it long ago. Inside this deadly zone, the planet's outer atmosphere swells and leaks into space. When the Hubble Space Telescope observed WASP-12b in 2010, scientists were startled to see clouds of glowing gas surrounding the system, forming a halo around the star. Upon closer study, they realized that this gas wasn't from the star at all. It was streaming from the planet itself. The outer layers of WASP-12b had expanded so far that they exceeded the planet's own gravitational boundary, spilling hydrogen and helium into space like a cosmic waterfall. The result was a steady stream of material flowing toward the star, creating a faint, glowing disk that encircled it. Some astronomers described this phenomenon as a planet bleeding into its sun. Others called it a world stretched like taffy under its star's glare. These comparisons, though poetic, are remarkably accurate. The same gravitational forces that raise Earth's tides are generating unimaginable internal friction within WASP-12b, heating it from the inside and driving gas outward. The closer it orbits, the stronger these forces become. It's a vicious cycle. The more the planet deforms, the more material it loses, and the more vulnerable it becomes to the same forces pulling it apart. In the simplest terms, the planet is feeding its star. The story of the Roche limit began nearly 2 centuries ago. In 1848, French astronomer Edouard Roche studied how a moon or satellite might behave if it orbited too close to a planet. His calculations revealed that past a certain distance, tidal forces would overwhelm the satellite's self-gravity, tearing it to pieces. This explained why Saturn's majestic rings exist. Rather than forming a moon, the material within Saturn's Roche limit was shredded into billions of icy fragments orbiting the planet. Now, astronomers were seeing that same physics at work on a planetary scale. But this time, the victim was not a small moon. It was a massive gas giant. WASP-12b thus became the first known exoplanet to orbit inside its Roche limit, giving scientists their first real-time view of planetary destruction. It showed what happens when gravity's nurturing hand turns cruel. Gravity, after all, is both creator and destroyer. It builds stars, shapes galaxies, and binds solar systems together. But when proximity becomes too intimate, its grip becomes lethal. On WASP-12b, this truth is undeniable. The planet's outer layers are caught in a tug-of-war, its own gravity struggling to hold them in while the star's pull rips them away. The result is a luminous stream of gas spiraling toward the star, forming an accretion disk that glows faintly as the stolen atmosphere burns in the stellar heat. Every second, WASP-12b loses billions of tons of gas. To put that in perspective, it's as if the planet was shedding an Earth's worth of atmosphere every few hours. At this pace, scientists estimate that the planet has only a few million years left before it's entirely consumed, a brief flicker of time on the cosmic clock. The process is neither explosive nor dramatic. Rather, it's a slow-motion death, a gradual unraveling of a world from the outside in. Scientists have described this process vividly. One likened it to taffy being pulled apart, the planet stretched on one side while bulging on the other as it tries to maintain its shape. The distortion produces powerful atmospheric currents, with winds racing across the surface at tens of thousands of miles per hour. Within this infernal environment, chemistry goes wild. Molecules that would remain stable on Earth are ripped apart by radiation, and exotic compounds form and dissolve in seconds. WASP-12b's atmosphere is not simply dying, it is transforming into something alien and chaotic, a living chemistry experiment conducted under unbearable heat. This grim spectacle forces astronomers to confront an uncomfortable truth about planetary stability. For decades, they believed that once a planet settled into an orbit, it would remain stable unless disrupted by a catastrophic event. A collision, a close gravitational encounter, or the death of its star. WASP-12b shattered that belief. Here was a gas giant that formed normally, likely far from its star, and then migrated inward over time through gravitational interactions. Once it crossed a certain threshold, the inward pull became irreversible. Now, it resides in a place where no planet should exist. Its continued presence inside the Roche limit defies every model of planetary physics. A gas giant this close should have been destroyed long ago. Yet somehow, WASP-12b persists, bloated, unstable, and fragile, but still intact enough for us to observe. In many ways, it's a cosmic contradiction, a world that shouldn't exist, surviving moment by moment in defiance of gravity itself. Despite its persistence, WASP-12b's fate is sealed. The gravitational forces stretching it are also robbing it of orbital energy, slowly dragging it closer to its star. With every orbit, completed in just over a single Earth day, the planet loses more angular momentum, inching toward its doom. Eventually, one of two outcomes awaits. The first is that the planet will spiral directly into its star, vanishing beneath the surface in a final, brilliant flare. The second, more likely scenario, is that the planet will be torn apart before reaching that point, leaving behind a faint, glowing ring of gas and debris, the ghostly remains of a once mighty world. Whichever outcome unfolds, the ending is the same: total annihilation. This process is not unique to WASP-12b. Astronomers now suspect that many close-orbiting exoplanets suffer similar fates. Yet WASP-12b's extreme conditions make it a rare and valuable subject of study, a front-row seat to the disintegration of a planet in real time. It offers insight into how planetary systems evolve and die, reshaping our understanding of cosmic lifespans. In studying WASP-12b, astronomers are, in essence, looking into the mirror of our eventual destiny. As the planet's gases drift away, they do not vanish into the void. Much of this material spirals inward, feeding the star that is consuming it. The star absorbs its planet's elements: hydrogen, carbon, and heavier metals, altering its own chemistry in the process. Over time, the star becomes a hybrid of itself and its victim, enriched by the remains of the world it destroyed. Astronomers describe this as a kind of cosmic cannibalism, a star feasting on the very planet that once orbited it. It's a disturbing yet strangely poetic image, the ultimate cycle of creation and destruction. This strange coexistence raises another question: why does WASP-12b still exist at all? How can it survive even temporarily inside a zone that should have obliterated it? The answer may lie in the fluid nature of gas giants. Unlike rocky planets, gas giants lack solid surfaces, allowing them to deform and redistribute their mass under stress. This flexibility may grant WASP-12b a temporary reprieve, delaying total destruction. Yet even this resilience has limits. As the planet continues to lose mass, its ability to resist the star's pull diminishes, and soon it will no longer be able to hold itself together. When that moment comes, the planet will disintegrate into a glowing ring of debris, like a funeral wreath orbiting the star that consumed it. For astronomers, watching this process unfold is both haunting and extraordinary. WASP-12b offers an unparalleled opportunity to observe planetary death as it happens. Each time the planet passes in front of its star, telescopes detect subtle variations in brightness, tiny dips that reveal how much more gas has escaped and how much closer the planet has crept to its end. It's like watching the faint heartbeat of a dying world, pulsing weaker with every orbit. Future observations, especially with advanced instruments like the James Webb Space Telescope, are expected to reveal even greater detail. The chemical signatures of the escaping gases, the temperature distribution across the planet's surface, and the structure of the debris surrounding the star. Each discovery brings us closer to understanding not just how planets live, but how they die. The hellish atmosphere. WASP-12b's atmosphere is unlike anything the human mind can comfortably imagine. A furnace world where chemistry bends under heat and elements exist in states unknown on Earth. The planet is classified as a hot Jupiter, a gas giant that formed far from its parent star, but now circles so close that its outer layers are boiling away. The planet's day side is a roiling inferno, exposed constantly to the full intensity of its star's radiation. Temperatures exceed 4,000 degrees Fahrenheit, about 2,200 degrees Celsius, easily hot enough to melt or vaporize steel. At such extremes, even basic molecules struggle to survive. Hydrogen atoms separate from one another, carbon bonds are torn apart, and the atmosphere glows faintly from the energy it absorbs. The atmosphere is primarily composed of hydrogen and helium, much like Jupiter's, but that is where the resemblance ends. WASP-12b is so hot that these gases behave in extraordinary ways. The intense heat strips electrons from hydrogen atoms, creating a partially ionized plasma, a fluid state of matter rarely found outside stars. This plasma interacts with the planet's magnetic field, generating a faint electromagnetic glow that can be detected from across light years. Embedded within this volatile mix are heavier molecules, such as carbon monoxide, which dominate the chemistry of the planet's upper layers. Carbon monoxide forms because oxygen prefers to bond with carbon at these temperatures, leaving little free oxygen for water vapor to exist. As a result, the atmosphere is likely dry, devoid of clouds or the reflective mists seen on cooler exoplanets. The intense heat also ensures that the boundary between day and night is extreme. The planet's orbit is so tight that it has become tidally locked, meaning one hemisphere always faces the star while the other remains in perpetual darkness. On the day side, temperatures soar above 4,000 degrees Fahrenheit, but the night side, though cooler, still bakes at thousands of degrees. This contrast creates violent winds that scream across the planet at several miles per second, redistributing heat in chaotic currents. Observations from the Spitzer Space Telescope have revealed that the planet's hottest point isn't directly beneath its star, as physics would suggest, but slightly shifted. This offset indicates the presence of vast atmospheric jet streams carrying heat around the globe, an enormous furnace in constant motion. At these conditions, no solid surface could exist. The planet's outer layers are entirely gaseous, expanding outward like a balloon under pressure. Even at great depths, where gravity compresses the gas into liquid metallic hydrogen, the heat prevents stability. The upper atmosphere itself glows faintly, radiating infrared energy back into space. In visible light, the planet reflects almost nothing. It is one of the darkest worlds ever discovered, absorbing nearly all the starlight that hits it. This makes WASP-12b appear more like a smoldering ember than a shining planet, its faint red glow marking the thin line between planet and star. Astronomers studying its spectrum have detected hints of carbon-rich chemistry, suggesting that the ratio of carbon to oxygen in WASP-12b's atmosphere may be higher than that of our Sun. This single detail changes everything. A carbon-dominated environment means the potential for exotic compounds such as methane, acetylene, and cyanide gases, substances that can only exist briefly before being shredded by ultraviolet radiation. The presence of these molecules points to a history of violent migration. A planet that once formed far from its star, where carbon was plentiful, now dragged inward to a region where it cannot survive. The upper atmosphere, constantly blasted by stellar radiation, swells and expands outward into space. Hydrogen atoms escape at incredible rates, forming a comet-like tail that trails behind the planet along its orbit. In ultraviolet observations, this tail appears as a faint haze, a stream of matter stripped from the planet and scattered through the system. It's not just atmospheric loss, it's atmospheric disintegration on a planetary scale. The outflowing gases are ionized, forming a sheath of charged particles that interact with the star's own magnetic field. The result is a kind of electric dance, a continuous exchange of particles between planet and star, blurring the boundary between where one ends and the other begins. Within this dynamic environment, temperatures fluctuate violently with altitude. Near the upper layers where radiation dominates, heat ionizes molecules and drives supersonic winds. Deeper down, pressure increases dramatically, compressing gases into dense, superheated layers that might resemble liquid metal. Even the concept of a sky becomes meaningless. There is no point where gas gives way to solid ground, only deeper and deeper layers of crushing pressure. A spacecraft descending into WASP-12b would never land. It would simply sink and dissolve, its materials vaporized long before reaching the core. Observations also suggest that the planet's atmosphere may contain titanium oxide and vanadium oxide, both potent absorbers of heat. These compounds act like a thermal blanket, trapping radiation and preventing the planet from cooling efficiently. This effect, known as a temperature inversion, causes the upper atmosphere to become hotter than the layers below, a reversal of what happens on Earth. The inversion adds to the planet's overall instability, amplifying the destructive power of the star's radiation and accelerating the loss of material into space. Every orbit brings WASP-12b face-to-face with another blast of intense ultraviolet and X-ray radiation. The planet's close proximity means it receives thousands of times more stellar energy than Earth. This radiation breaks apart molecules, drives chemical reactions, and produces a haze of exotic compounds that absorb and re-emit light in unpredictable ways. For astronomers, Decoding these spectral signatures is like reading the autopsy report of a dying world. Each wavelength of light carries information about the gases being stripped away, the temperatures of the layers beneath, and the rate at which the planet's atmosphere is vanishing. At a distance of about 870 light-years from Earth, WASP-12b's light takes nearly a millennium to reach us, meaning that what telescopes see today is how it appeared nearly 1,000 years ago. The planet could already be dramatically different or gone entirely. Yet even across this gulf of time and space, the signals it sends tell a clear story. Its atmosphere is being destroyed faster than any known exoplanet. The delicate balance between gravity and heat has already tipped beyond recovery. The night side of WASP-12b offers no comfort. While shielded from direct starlight, the planet's internal heat, generated by tidal distortion and atmospheric friction, keeps temperatures high enough to vaporize most known metals. Iron, sodium, and magnesium that might exist deeper down rise as vapors, condensing only in the brief twilight regions where day meets night. These boundary zones may experience bizarre chemical transitions, metallic clouds forming, glowing faintly, and evaporating within hours as they circulate back into the light. For a brief moment, they shimmer against the horizon, only to be torn apart again by wind and heat. Because of the immense pressure and radiation, even the notion of color becomes alien here. The atmosphere might appear black, not because it is dark, but because it absorbs nearly every wavelength of visible light. Any reflection would be swallowed by the sheer depth of the heat and gas. Only in infrared does the planet truly shine, radiating the energy it cannot hold. It is a world glowing from its own torment, a beacon of heat surrounded by darkness. In this extreme environment, conventional meteorology has no meaning. There are no clouds, storms, or rain as we understand them, only waves of gas shifting under constant stress. If weather exists, it is measured in the movement of plasma currents and the migration of chemical bands across the planet's circumference. In a sense, WASP-12b's entire atmosphere is one continuous storm, powered by forces beyond comprehension. These findings have challenged everything astronomers thought they knew about planetary atmospheres. Before the discovery of hot Jupiters like WASP-12b, it was assumed that giant planets could not exist in such close proximity to their stars. The expectation was that they would form far away, where gases could condense and remain stable. WASP-12b upended that logic, forcing scientists to reconsider the possibilities of planetary formation, migration, and survival. The chemistry of its atmosphere, its metallic gases, ionized hydrogen, and carbon dominance provides crucial data for understanding how worlds evolve under extreme conditions. Every observation of WASP-12b feels like catching a moment in a disaster that has no pause. Astronomers can map its chemical composition, model its temperature gradients, and measure the speed of its escaping gases. But none of these efforts can alter the fact that the planet's atmosphere is doomed. The process is irreversible. The outer layers continue to expand, heat continues to rise, and radiation continues to erode what remains. The irony is that this destruction makes WASP-12b easier to study. The escaping gases form a kind of luminous shroud that amplifies its signal, allowing telescopes to detect its presence even when the planet itself is nearly invisible. In this way, the very forces that are killing the planet also reveal its secrets to those watching from afar. WASP-12b's atmosphere is not simply hot, it is hostile to matter itself. Every particle exists on the edge of destruction, and every orbit renews that violence. The heat that drives the winds, strips the gases, and glows through space is both the symptom and the cause of its unraveling. It is a reminder that even the grandest planets, built from the same cosmic dust as stars, can burn too brightly, live too close, and die too soon. When astronomers first measured WASP-12b's albedo, the fraction of light a planet reflects, they were stunned. The readings didn't just come back low, they came back nearly non-existent. WASP-12b reflects barely 6% of the light that hits it, meaning it absorbs 94% of everything its star emits. For perspective, that's darker than fresh asphalt, darker than charcoal, darker even than most black holes' accretion disks from a reflective standpoint. No other planet observed in the visible spectrum has ever been this black. It became known as the darkest world ever found, a light-eating sphere that seemed to defy reason. For scientists who study planetary atmospheres, the discovery was both exhilarating and deeply unsettling. Planets, even the hottest ones, tend to reflect at least some portion of their star's light, through clouds, atmospheric haze, or molecular scattering. But WASP-12b offered nothing. It was as if the planet swallowed light whole, devouring every photon that touched it. When the data first arrived from the Hubble Space Telescope and the Spitzer Space Telescope, many astronomers thought there had been a calibration error. The measurements made no sense. A gas giant that black shouldn't exist, not under any known atmospheric model. One of the first researchers to review the data described the reaction as disbelief mixed with awe. A planet that shouldn't be able to exist, and yet there it was, invisible, one scientist reportedly said during an early debriefing. The planet's orbit was well established, its transits clear, its size measurable, and yet in reflected light, it practically disappeared. That contradiction, a world so big and bright in infrared but vanishingly dark in the visible spectrum, shattered expectations. The darkness of WASP-12b isn't a coincidence. It's a direct result of its extreme environment. In most planetary atmospheres, clouds or hazes form as light elements condense, reflecting starlight and scattering photons back into space. But at 4,000 degrees Fahrenheit, 2,200 degrees Celsius, the atmospheric gases on WASP-12b are too hot for any kind of condensation. There are no reflective cloud decks made of silicates or metals, no high-altitude aerosols to bounce light away. Instead, light plunges deep into the planet's atmosphere, where it's absorbed by molecules and atoms and converted into heat. At these temperatures, hydrogen gas becomes an excellent absorber, and the addition of carbon compounds makes things worse, or more accurately, darker. The atmosphere likely contains long chains of carbon molecules known as polycyclic aromatic hydrocarbons, similar to the sooty compounds that form in flames on Earth. These molecules are efficient light sponges. They trap visible wavelengths and re-radiate them in infrared. In other words, WASP-12b doesn't reflect light. It transforms it into heat, glowing faintly in wavelengths human eyes can't see. To put it simply, the planet is a black-body radiator in motion. Its surface isn't black because it's cold or inert. It's black because it's too hot. The atmosphere's structure absorbs energy at every layer, and whatever light it releases escapes as invisible thermal radiation. From an optical perspective, the result is haunting. A massive gas giant orbiting a brilliant star, yet appearing as an absence of light, a void. This characteristic alone makes WASP-12b a cosmic anomaly. When scientists modeled its spectrum, they expected some degree of reflection or scattering, perhaps from metal oxides like titanium or aluminum compounds. Instead, they found an almost featureless blackbody curve, as if the planet were a perfect absorber. The lack of spectral features suggested that even trace elements were being broken down, leaving a chemical soup dominated by ionized hydrogen and carbon monoxide. In visible light, the planet is nearly invisible against the glare of its star, which complicates direct imaging. Astronomers had to rely on transit observations, watching how the star's light dimmed slightly as the planet passed in front of it, and how it brightened again once the planet moved away. The minuscule difference in light before and after these events revealed just how little reflection the planet produced. It was like watching a shadow move across a floodlight, the shadow itself swallowing rather than blocking the light. What made this discovery so unsettling was how it challenged existing models of planetary albedo. Before WASP-12b, the darkest known exoplanets, such as TRES-2b, reflected about 1% of their starlight. That was already considered extreme. But WASP-12b's near-total absorption pushed the limits of what physicists believed possible for an atmosphere composed of hydrogen and helium. Some theorized that the planet's extreme gravity might compress its atmosphere in such a way that scattering was minimized. Others proposed that the planet's composition was unusually carbon-heavy, producing a kind of natural soot that coated its upper layers. Another possibility lay in the planet's temperature distribution. Because WASP-12b is tidally locked, its day side faces the star continuously, while the night side remains perpetually dark. The day side may be so hot that gases are thermally ionized, electrons stripped from atoms, creating an ionosphere capable of absorbing nearly all incoming radiation. Without reflective molecules or stable bonds, light simply disappears into the plasma. The night side, meanwhile, would re-radiate the absorbed energy slowly in infrared, glowing faintly, but still remaining dark to human eyes. To confirm these hypotheses, scientists turned to high-precision instruments capable of measuring light across multiple wavelengths. Observations from the Hubble Space Telescope's Cosmic Origin spectrograph confirmed that WASP-12b's atmosphere was indeed carbon-rich, supporting the theory of soot-like absorption. Infrared data from Spitzer further revealed that the planet's thermal emission matched a near-perfect blackbody, meaning it was re-emitting energy uniformly, without the variation typical of reflective clouds. Every photon that hit the planet was effectively trapped and then released as heat. These findings unsettled researchers because they implied a level of atmospheric homogeneity rarely seen in nature. Planets usually have variations, cloud belts, storms, and chemical gradients that scatter light differently at different altitudes. WASP-12b, by contrast, seemed stripped of complexity, reduced to a single function, to absorb. It was, in effect, a cosmic sponge. The very property that made it fascinating to study also made it deeply eerie to imagine. Astronomers who specialize in exoplanet atmospheres often describe their work as remote sensing of alien weather. Yet WASP-12b resists such familiar language. There is no weather there as we know it, no variation in albedo, no bright clouds reflecting a sunrise or sunset. Every square mile of its surface, if it can even be called a surface, behaves the same way, devouring light and radiating heat. The absence of reflective features makes it appear uniform, a featureless void wrapped around a dying world. Even stranger, the lack of reflected light may play a role in the planet's accelerated death. By absorbing almost all incoming energy, WASP-12b heats more efficiently, expanding its outer layers and making it easier for its star to strip them away. In essence, its darkness is hastening its destruction. The darker it is, the faster it dies. This cycle, absorb, expand, evaporate, creates a self-destructive feedback loop that ensures its eventual consumption by its parent star. The scientists observing this process often speak of it in paradoxical terms: a planet too bright to see, too dark to detect. The only reason we know it exists is because of the tiny fluctuations it causes in its star's light. In direct imaging, it would be invisible, its darkness blending seamlessly with the void of space. The star, WASP-12, shines brilliantly, but its companion remains unseen, a phantom orbiting at suicidal proximity. To make sense of this phenomenon, researchers began comparing WASP-12b to materials on Earth that exhibit similar properties. The closest analogues are Vanta black and other synthetic ultra-black coatings, materials designed to absorb up to 99.9% of visible light. These substances work by trapping light within microscopic cavities, preventing it from escaping. On WASP-12b, the same effect is achieved naturally, not through structure but through chemistry and heat. Its gases act as a vast, dynamic absorber, each molecule contributing to the annihilation of light. This parallel fascinated the public imagination. When news outlets reported that astronomers had found the darkest planet in the universe, it sounded like science fiction, a world made of shadow orbiting too close to its sun. Yet the truth was even stranger. WASP-12b is not dark because it is dead. It is dark because it is too alive, too active, too overwhelmed by its environment to let light escape. Its darkness is the result of pure, unrestrained energy. As more data arrived, scientists began mapping how the absorbed light was re-emitted. The planet's infrared spectrum revealed that the energy didn't distribute evenly. Instead, it pulsed subtly with each orbit, suggesting fluctuations in atmospheric density and heat transfer. These small variations hinted at chaotic internal dynamics, waves of expansion and contraction rippling through its layers. The picture that emerged was not of a static world, but of one constantly convulsing under the strain of its own heat. Every discovery about WASP-12b's light absorption led to new questions. Why didn't similar planets display this degree of darkness? Why was the carbon so abundant here and not elsewhere? Did the planet form in a region of its system unusually rich in carbon? Or did it acquire that composition after migrating inward and losing its lighter elements? These questions remain open, but one thing is clear. WASP-12b's opacity is not an anomaly. It's a consequence, a symptom of a planet pushed to its limits. Astronomers continue to point telescopes at this strange world, not because they expect to find life or even long-term stability, but because it provides a rare opportunity to study physics at its extremes. In WASP-12b, light meets its end not in the crushing gravity of a black hole, but in the suffocating embrace of a dying gas giant. Each photon that enters its atmosphere tells a story of destruction, transformation, and decay. Even now, years after its discovery, WASP-12b remains a source of fascination and unease. Every new analysis confirms that it is the blackest planet ever recorded, a true cosmic oddity. The darkness that once seemed like a mystery is now understood as a kind of cosmic efficiency, an atmosphere that wastes nothing, reflects nothing, and endures nothing. To gaze at WASP-12b through the lens of modern astronomy is to confront a world that doesn't simply defy expectations. It absorbs them. The planet that's being devoured. The Hubble Space Telescope's ultraviolet spectrograph first revealed the unthinkable. Streams of gas flowing away from the planet, not in random bursts, but in a coherent curved arc, a structure known as an accretion disk, the kind of formation usually found around dying stars or black holes. This was not supposed to happen around a living star with a planet still in orbit. Yet there it was, clear evidence that the planet's own star had begun to eat it alive. For context, the gravitational pull of a star like WASP-12 is immense, far beyond what a gas giant like WASP-12b can withstand at such close range. The planet orbits just 2 million miles away, closer than any of our solar system's planets are to the Sun by a staggering margin. At that proximity, the planet's outer layers are no longer gravitationally bound to its core. Instead, the material is stripped away by the star's tidal forces, drawn outward and captured by the star's gravity. This is what forms the glowing halo of gas seen around the system. To scientists, it was both mesmerizing and horrifying. They were watching, in real time, a planet die. When Hubble's data first came through, researchers noticed that the planet's transit, the moment it passed in front of its star, appeared to dim the star's light by a slightly greater margin than expected. The effect was wavelength dependent, meaning the planet's atmosphere was not only absorbing light, but scattering it differently depending on its composition. That clue led to the discovery of something extraordinary. The planet's atmosphere was no longer confined to the planet itself. It extended far beyond, stretching into space like a comet's tail. This wasn't a stable atmospheric layer. It was gas in motion, racing away from the planet under the intense heat and gravitational forces. Hydrogen atoms were the first to escape, followed by traces of helium and heavier molecules like carbon monoxide. Hubble's ultraviolet sensors captured this gas as it streamed outward, wrapping around the planet and forming a faint glowing disk of stellar material. In a way, WASP-12b had stopped being a planet in the traditional sense. It was becoming an ingredient, a part of its star's outer environment. The material it lost was being recycled into the stellar system, possibly altering the star's own chemistry over time. Astronomers were witnessing stellar cannibalism, not between two stars, but between a star and its unfortunate planet. The Spitzer Space Telescope, which observes in infrared light, later confirmed the process. It detected heat signatures consistent with dust and gas circling WASP-12, exactly like the accretion disks seen around young stars forming new planets. But in this case, it wasn't creation. It was destruction. The data painted a grim picture. Every second, the star WASP-12 siphoned away hundreds of thousands of tons of the planet's atmosphere. It's a process so violent that the planet's orbit itself is decaying, inching it ever closer to its demise. Scientists estimate that within 3 to 10 million years, a blink in cosmic time, WASP-12b will cease to exist altogether. The planet's surface, if one can even call it that, is a roiling sea of plasma and superheated gases. Winds blow faster than sound, carrying material toward the star's gravitational well. From above, the planet would resemble a glowing ember wrapped in smoke, trailing a plume of matter that stretches across thousands of miles. Hubble's ultraviolet imaging captured the faint silhouette of that trail, a diffuse, ghostly structure that seemed to bridge the gap between the planet and the star. For astronomers, it was the moment of consumption immortalized in light years of distance. WASP-12b is not alone in its fate, though it remains the most dramatic example of a planet being devoured by its star. Other doomed worlds exist, smaller, less spectacular perhaps, but no less tragic. One of the most notable is Kepler 1520b, a rocky planet orbiting so close to its star that it sheds dust and rock fragments into space, forming a visible trail behind it. Unlike WASP-12b, which is a gas giant, Kepler 1520b is a disintegrating world, a planetary ember losing mass every orbit until nothing remains. There's also NGTS-10b, another ultra-hot Jupiter that completes an orbit in just 18 hours. Its day side is scorched beyond recognition, and scientists predict it, too, will eventually be torn apart. Each of these discoveries underscores the same haunting reality. Planets can die, and the universe is not kind in how it erases them. But what makes WASP-12b stand out is the clarity with which we can observe its death. Never before have astronomers been able to measure in such detail the precise way a planet's material transfers to its host star. The system provides a rare, almost voyeuristic glimpse into a cosmic process that was once purely theoretical. It's as though the universe has allowed humanity to peek behind the curtain, to witness the last act of a world's existence. The accretion process surrounding WASP-12b isn't entirely silent. As the planet's gases spiral into the star, they heat up through friction and compression, releasing radiation that can be detected across various wavelengths. This radiation gives astronomers critical clues about the rate of mass loss and the composition of the escaping atmosphere. Some estimates suggest that the planet loses about 189 quadrillion tons of gas every year, a rate so extreme that the planet visibly inflates, becoming more ablate and elongated as its atmosphere thins out. Over time, this creates a feedback loop. As the atmosphere escapes, the planet's density decreases, making it even more susceptible to the star's pull. It's the cosmic equivalent of a candle burning faster the smaller it becomes. And yet, despite this chaos, the system remains strangely stable for now. The planet continues to orbit day after day, its existence defined by the very forces that are destroying it. The spectacle has made WASP-12b one of the most closely studied exoplanets in astronomy. Not just because of its death, but because of what that death can teach us. For scientists, WASP-12b is more than a curiosity. It's a laboratory. By studying how its atmosphere behaves under extreme heat and gravitational stress, astronomers can refine models of planetary evolution and atmospheric escape. These findings help predict the fates of other exoplanets, including those that might one day suffer a similar end. The data also reveal how stars themselves evolve when fed by planetary material. When a star consumes a planet, it can temporarily brighten, its spectrum shifting as it absorbs new elements. These changes might be subtle, but they can serve as cosmic fingerprints, allowing future astronomers to identify other stars that have devoured their worlds. In this way, WASP-12b becomes a key to understanding the long-term dance between stars and their planets. It shows that even the most stable-seeming systems are fragile, and that the line between survival and destruction in the cosmos is thin. And though its fate is sealed, WASP-12b continues to fascinate, spinning endlessly on its doomed orbit, a planetary ghost circling the fire that will one day consume it. Each pass brings it closer to the inevitable, each observation offering a new glimpse into the mechanics of cosmic death. For astronomers peering through the vastness of space, watching that faint light dip and return again, the realization is both humbling and terrifying. The universe gives and the universe takes, and even the giants are not spared. The dark side mystery. When scientists first began mapping the surface temperatures of WASP-12b, they expected a predictable pattern: heat radiating from the star-facing side and dispersing evenly across the rest of the planet through fierce winds and jet streams. After all, gas giants are known for their chaotic weather systems. On Jupiter, for instance, colossal storms like the Great Red Spot rage for centuries, redistributing energy across thousands of miles. Even on the tidally locked planets discovered before WASP-12b, there was at least some evidence of atmospheric circulation, hot air moving to the dark side, cooling, and then cycling back toward the star-facing hemisphere. But what they found on WASP-12b made no sense. The planet's day side was unimaginably hot, yet the night side, the hemisphere eternally turned away from its star, was surprisingly cooler. This wasn't just a minor temperature difference. It was a sharp divide between a blazing inferno and a realm of relative calm, as though the planet's two halves belonged to entirely different worlds. This stark contrast puzzled scientists. It meant that the planet wasn't distributing heat as expected. Something was trapping the energy on one side, turning the entire world into a thermal paradox. WASP-12b is tidally locked, meaning one side perpetually faces its star, while the other remains in eternal night. This is a common occurrence among close-orbiting exoplanets, where the gravitational interaction between the planet and its star gradually slows the planet's rotation until one hemisphere is forever sunlit and the other is trapped in endless darkness. Earth's moon behaves the same way. One side always faces us. But on WASP-12b, this locking comes with deadly consequences. On the day side, the radiation from its parent star is relentless. The heat is so intense that molecules struggle to remain intact. Hydrogen atoms split apart, clouds cannot form, even reflective compounds like silicates and titanium oxides, which could have bounced some light away, are vaporized. As a result, the atmosphere becomes a smooth, featureless ocean of superheated gas that absorbs nearly all incoming radiation. No reflective clouds, no scattering particles, just a black, light-eating surface. The night side, meanwhile, is shrouded in perpetual darkness, deprived of direct starlight. In theory, winds should whip around the planet at supersonic speeds, transporting some of the heat from the day side and raising the temperature there. But observations revealed something odd. The heat simply wasn't making the journey. The night side remained dramatically cooler, as if some invisible barrier separated it from the blistering half just beyond the horizon. This imbalance suggested that WASP-12b's atmospheric dynamics were broken, or at least profoundly different from what any known model could predict. To understand why this baffled scientists, it helps to consider what normal looks like on a hot Jupiter. On most of these gas giants, intense heat on the day side creates high-pressure zones that push air toward the cooler, low-pressure regions of the night side. The result is a constant, turbulent flow of gas around the planet, jet streams capable of moving faster than 3,000 miles per hour. This circulation helps distribute heat more evenly, leading to relatively small temperature differences between hemispheres. But WASP-12b defied this rule. When astronomers used the Spitzer Space Telescope to observe the infrared emissions, essentially measuring heat directly, they found a thermal map with no evidence of significant energy transport. The planet's hottest region lined up exactly with the point facing the star, and there was almost no thermal offset. That meant there were no strong winds carrying heat away. The energy was trapped, suffocating the atmosphere under its own pressure. One leading theory proposes that WASP-12b's atmospheric composition may contain exotic carbon-based molecules, the same compounds that contribute to its pitch-black color. These molecules could be absorbing light and energy so efficiently that the planet's upper layers become dense and sluggish, preventing large-scale atmospheric motion. In essence, the planet's skin is so hot and opaque that energy simply can't move through it fast enough. The discovery that WASP-12b absorbs 94% of the light that hits it was already shocking. In terms of reflectivity or albedo, that's about as dark as it gets. For comparison, fresh asphalt reflects around 4–10% of visible light. WASP-12b is darker than that. Even black coal looks bright next to it. Scientists were stunned. A planet this large, orbiting this close to its star, should be gleaming like a mirror. Instead, it was almost invisible against the blackness of space. The darkness was not just a visual oddity, it was a clue. The planet's lack of reflection meant that nearly all the radiation it received was being absorbed as heat, but without an efficient way to transport that heat to the night side, or to radiate it back into space, the planet effectively became a trap. Its day side baked under the relentless energy of its star, while its night side lingered in relative coolness, locked in an eerie, unmoving equilibrium. When astronomers modeled this energy distribution, they realized that WASP-12b's atmosphere might act more like a thick syrup than a swirling gas. The immense pressure and temperature could make it viscous, less able to flow freely from one region to another. If true, this would explain why the heat doesn't circulate. The atmosphere itself is too heavy, too saturated with radiation to move quickly. The thermal behavior of WASP-12b has forced astronomers to reconsider how extreme environments can reshape planetary dynamics. Normally, atmospheric circulation is driven by convection, the movement of hot air rising and cool air sinking. But on WASP-12b, the constant unending heat on one side prevents that cycle from working properly. Instead of circulating, the air becomes stagnant, creating an almost static shell of trapped energy. This discovery challenges even the most advanced atmospheric models. Some researchers now suggest that the planet's upper layers may act like a reflective barrier for infrared energy, bouncing it inward rather than outward. Others propose that the carbon-heavy atmosphere could contain large, complex molecules similar to soot, which absorb radiation but emit very little in return. This would further enhance the planet's darkness while amplifying the thermal divide. Whatever the explanation, WASP-12b represents a failure of equilibrium, a world where physics still applies, but in ways that push it to its breaking point. If one could somehow hover above the planet, the sight would be unlike anything else in the galaxy. The day side would be a blinding furnace, glowing faintly in the ultraviolet spectrum, a sea of vaporized hydrogen and helium stretched thin under gravity's pull. On the horizon, where day meets night, there would be a sharp, burning line, a perpetual twilight of superheated gas cooling and collapsing into shadow. And beyond that line, the night side would vanish into blackness, cloaked in an eerie stillness where starlight never reaches. The contrast is not just thermal, but existential. One half burns in unending light, the other exists in frozen silence. And yet, both sides share the same doomed fate, slowly orbiting toward annihilation, pulled closer with every passing year. Astronomers sometimes refer to this kind of world as a two-faced planet. It's an evocative phrase, but it hardly captures the violence of what's really happening. WASP-12b isn't just divided by light and dark, it's being torn between two extremes, one that vaporizes and one that suffocates. The more scientists study WASP-12b, the more they realize how finely balanced planetary survival can be. If a gas giant drifts even slightly too close to its star, it risks crossing a threshold where its atmosphere becomes unstable. At that point, it no longer behaves like a planet but like a comet, shedding mass, losing energy, and eventually disintegrating. WASP-12b is teetering on that edge. Its darkness, its lack of heat transfer, its tidal distortion, all are symptoms of a planet existing in the narrowest possible margin between stability and destruction. And while its bizarre properties continue to fascinate researchers, they also serve as a warning. Worlds like this remind us that cosmic balance is fleeting. Even a planet 10 times the mass of Jupiter can crumble under the relentless pull of its own sun. Scientists describe the experience of studying WASP-12b as watching a slow-motion catastrophe, a world trapped in an endless feedback loop of heat and gravity, each cycle bringing it closer to its end. Its dark side, cool and hidden, may be the only part of the planet that still resists its star's fury. But even that sanctuary is temporary. As the planet spirals inward, the boundary between light and shadow will vanish, swallowed by the expanding reach of the star's radiation. Theories behind the darkness. Astronomers began to formulate theories, each stranger than the last. Some proposed exotic atmospheric chemistry, a chemical cocktail unlike anything found in our solar system. Others suggested that the planet's lack of clouds or reflective aerosols left it completely exposed, turning its surface into a light trap. A few even speculated that the atmosphere might be so carbon-rich that it behaves more like tar than gas, absorbing light in wavelengths that should normally scatter. Each hypothesis pushed planetary science further into the unknown. One of the most intriguing theories centers on the idea that WASP-12b's atmosphere is dominated by carbon rather than oxygen. On Earth, and in most known planets, oxygen plays a vital role in shaping atmospheric chemistry, combining with hydrogen to form water vapor, or bonding with metals and silicates to produce reflective clouds. But WASP-12b seems to operate under an entirely different set of rules. Spectroscopic data, light signatures captured when the planet transits its star, suggest unusually high levels of carbon-bearing molecules like methane, CH4, and carbon monoxide, with comparatively little water vapor. This imbalance points to a carbon-to-oxygen ratio greater than 1, meaning there's more carbon than oxygen in the planet's composition. If true, this would make WASP-12b one of the first known carbon-rich planets in the galaxy. Such worlds are theoretical oddities. Instead of silicate clouds, their upper atmospheres might contain carbon compounds like graphite or even microscopic diamond dust. But in WASP-12b's case, those materials never have the chance to condense. The extreme heat near the star prevents solid particles from forming, leaving the planet's sky cloudless and bare. The result is an atmosphere filled with gaseous carbon molecules that absorb light at nearly every visible wavelength. It's a perfect storm for darkness. Carbon-based molecules, particularly long-chain hydrocarbons, are notorious for their ability to absorb light rather than reflect it. They act like cosmic soot, capturing photons and converting them into heat. In fact, the planet's suffocating blackness might stem from the same fundamental physics that makes smoke appear dark on Earth. Only here, the smoke isn't a byproduct. It is the atmosphere. This chemical makeup challenges almost every conventional model of planetary formation. For decades, scientists believed that carbon-rich planets should be rare, since most stars, including our Sun, form in oxygen-dominated environments. But if WASP-12b's composition is truly carbon-heavy, it suggests that its star system formed from a different kind of nebular material, one richer in carbon compounds, or one that evolved in isolation from typical stellar nurseries. If confirmed, that would mean WASP-12b isn't just strange in its behavior. It might represent a completely new class of worlds. Another explanation for WASP-12b's darkness focuses less on its chemistry and more on its structure, specifically the complete absence of reflective clouds. Most hot Jupiters, even those orbiting extremely close to their stars, still manage to retain some kind of reflective haze or cloud layer. These clouds, formed from metallic oxides, silicates, or other exotic particles, scatter sunlight and give planets a brighter appearance. Jupiter, for example, owes its bright bands to layers of ammonia ice and other compounds high in its atmosphere. But WASP-12b appears utterly cloudless. At temperatures exceeding 4,000 degrees Fahrenheit, 2,200 degrees Celsius, any molecules that could form clouds are instantly vaporized. Titanium oxide, a compound known to reflect light on other hot planets, breaks apart into simpler gases. Silicates, which could have formed bright reflective layers, are stripped of their structure by intense radiation. Even metals that might condense into droplets are ionized, leaving behind nothing but bare, light-absorbing gases. Without clouds, the planet's atmosphere becomes a direct absorber, an unbroken ocean of gas that captures radiation at every level. There's no mirror layer to bounce light back. Instead, photons enter and never return. This lack of reflective aerosols explains why the planet is not only dark, but also so thermally unstable. Clouds usually help regulate a planet's temperature by reflecting energy outward, acting as a planetary thermostat. Without them, WASP-12b's day side becomes a heat sink, absorbing everything and radiating it back as infrared energy. But because there's so little heat circulation to the night side, most of that radiation escapes directly into space, preventing the planet from reaching any sort of equilibrium. The result is an atmosphere perpetually locked in a chaotic balance between absorption and emission, a thermal tug-of-war with no end. One of the more daring theories proposed by planetary chemists is that WASP-12b's atmosphere might resemble a kind of cosmic tar, a mix of dense hydrocarbon-rich gases that behave almost like a liquid under high pressure. At the temperatures found on WASP-12b, complex carbon chains such as polycyclic aromatic hydrocarbons, PAHs, could form in large quantities. These molecules are incredibly efficient at absorbing light, and their presence could explain the planet's almost total lack of reflectivity. If this hypothesis is correct, then WASP-12b's upper atmosphere might look less like a clear gas and more like a smog-filled haze. Imagine a world where the air itself glows faintly red from heat, but light cannot penetrate more than a few miles before being swallowed. It's a place where visibility would be measured not in distance, but in seconds, how long it takes before photons vanish into the dense soup of carbon chemistry. This tar planet idea remains speculative, but it fits the data. The planet's emission spectrum, the light it emits due to its own heat, shows unusual patterns, inconsistent with any known atmospheric model. The carbon-rich, aerosol-free hypothesis explains both the darkness and the lack of detectable water vapor or reflective compounds. It also suggests something more profound, that WASP-12b may be chemically alien to anything in our solar system. We often think of exoplanets as distant versions of our familiar worlds, Jupiters, Neptunes, or Earths orbiting other stars. But WASP-12b challenges that notion. Its chemistry doesn't just differ by degree, it differs by kind. It may represent an entirely new category of planetary existence. Every observation of WASP-12b has forced astronomers to rewrite the equations that govern planetary atmospheres. Early models assumed that hot Jupiters, regardless of their proximity to their stars, would follow predictable thermal patterns based on convection and molecular composition. WASP-12b shatters those assumptions. For one, the carbon-heavy atmosphere means that the planet doesn't fit into the typical framework of hydrogen-dominated gas giants. The balance of elements changes everything: how heat is distributed, how light is absorbed, and how molecules react at extreme temperatures. Standard computer simulations used to predict the appearance and behavior of exoplanets simply don't work when applied here. They produce results that contradict observed data. In many ways, WASP-12b has become a proving ground for astrophysical theory, a place where the limits of chemistry, thermodynamics, and gravitational dynamics collide. Researchers now use it as a benchmark for testing new atmospheric models designed to handle the most extreme conditions imaginable. These next-generation models take into account carbon enrichment, molecular dissociation at high temperatures, and even ionized metallic gases that interact with stellar radiation in unpredictable ways. One striking realization from these models is that planets like WASP-12b may not be rare at all. We've simply been unable to detect most of them because their black, light-swallowing surfaces make them nearly invisible. They could be orbiting countless stars across the galaxy, hidden in plain sight, their darkness concealing them even from our most powerful instruments. The more scientists study the planet's chemistry, the stranger it becomes. Normally, a planet's atmosphere reaches a kind of equilibrium where the ratios of gases like methane, carbon monoxide, and water vapor stabilize according to temperature and pressure. But WASP-12b refuses to cooperate. Instead, it shows evidence of what's called non-equilibrium chemistry, a state where reactions occur faster than the atmosphere can balance them. In other words, the planet's gases are constantly shifting between molecular states, never settling into a steady composition. The intense radiation from its star bombards the atmosphere, breaking apart molecules and forcing them into new, unstable forms. This endless chemical churn might be one reason why clouds never form. Molecules that could have condensed into particles are destroyed before they have the chance. The same process may also contribute to the planet's strange emissions, irregular spikes in infrared radiation that don't match the expected heat patterns. WASP-12b's atmosphere in this sense behaves almost like a living system, dynamic, chaotic, constantly changing. It's a laboratory for chemical extremes, where traditional ideas about stability and equilibrium simply don't apply. As astronomers continue to observe WASP-12b, they're realizing that this death planet may hold clues not just about planetary destruction, but also about creation. The presence of carbon-rich chemistry hints that worlds like this could form in very different environments, perhaps around stars with unique elemental ratios, or in regions of the galaxy where carbon dust dominates. If carbon worlds are more common than previously thought, it could change how we search for planets that might support life. After all, carbon is the building block of biology. A carbon-rich planet might not be habitable in the way Earth is, but it could demonstrate how the same element that forms the basis of life can also create the darkest, most hostile environments in the cosmos. The carbon enigma. When scientists first began dissecting the chemical makeup of WASP-12b's atmosphere, they were prepared for the usual suspects: hydrogen, helium, and trace elements resembling what is found in Jupiter or Saturn. But what they discovered challenged not only expectations, but also the very framework of planetary science itself. Observations indicated that this doomed gas giant possessed a carbon-to-oxygen ratio greater than 1. In simple terms, WASP-12b contained more carbon than oxygen, an astonishing revelation that made it unlike any world in our solar system. On Earth, and throughout our local planetary neighborhood, oxygen dominates. It's the key element that bonds with hydrogen to create water, with silicon to create rock, and with carbon to form carbon dioxide. Our planets and moons, from Venus to Neptune, follow this oxygen-heavy pattern. But a carbon-rich world, that was new territory entirely. For astronomers, this ratio changed everything. A carbon-dominated planet wouldn't be built from the same ingredients as ours. It would be fundamentally alien, sculpted by a chemistry no one had ever seen firsthand. At first, the readings didn't make sense. The atmosphere's spectral data, the unique fingerprint of light absorbed or emitted by its gases, suggested strong signs of carbon compounds such as methane, CH4, carbon monoxide, CO, and hydrogen cyanide, HCN. What stood out was not merely their presence, but their relative dominance compared to oxygen-bearing molecules like water vapor. In WASP-12b's atmosphere, water was scarce, a shocking absence given its abundance in most planetary atmospheres. This imbalance was the first major clue that something unusual was happening. The planet's chemistry hinted at formation conditions utterly different from those that gave rise to Jupiter or Saturn. The implications went far beyond the atmosphere. If WASP-12b truly had a carbon-to-oxygen ratio greater than 1, Its internal structure could be composed of carbon-based minerals, carbides, graphite, and perhaps even diamond. In cooler environments, where temperatures drop below thousands of degrees, carbon condenses into solid crystalline forms. This sparked a striking hypothesis. If a planet like WASP-12b existed farther from its star, at a comfortable distance where the inferno subsided, its clouds might literally rain diamonds. Deep within, the pressure could compress carbon into glittering layers, creating a diamond-encrusted world unlike anything in our own solar system. That vision, a planet shimmering beneath carbon storms, fired the imagination of scientists and dreamers alike. But beneath the wonder, there was unease. Such a carbon-rich world defied the standard model of planetary formation, which assumes that planets form in protoplanetary disks with similar ratios of carbon and oxygen as their parent stars. WASP-12, the star itself, didn't exhibit an unusual chemical imbalance. So how could its planet have such a skewed ratio? The question raised uncomfortable possibilities. Either the planet had somehow formed in a completely different environment and later migrated inward, or the chemistry of its atmosphere had been altered by the very process of its destruction. Some scientists proposed that as WASP-12b was being stripped by its star's gravity, its lighter oxygen-bearing compounds, like water vapor, were the first to be pulled away. The heavier carbon compounds, more resistant to escape, remained behind. Over time, this selective stripping would enrich the atmosphere in carbon, giving it the dark, sooty appearance that made the planet absorb almost all light. In essence, the planet's death could be reshaping its very chemistry. The carbon enigma might not represent how WASP-12b was born, but what it was becoming as it was devoured. Still, others weren't convinced. They argued that the planet's composition reflected its origins, not its demise. Perhaps WASP-12b formed in a region of its protoplanetary disk where carbon grains dominated and oxygen compounds had frozen out. In such a carbon-rich environment, the planet would naturally accumulate layers of graphite and silicon carbide, leading to its strange chemistry. If true, that would mean WASP-12b was part of a broader, more exotic family of exoplanets, carbon worlds, that could exist throughout the galaxy, hidden among the thousands of alien worlds waiting to be discovered. The idea of carbon worlds marked a paradigm shift in how astronomers viewed planetary diversity. For decades, they had assumed that planets everywhere would mirror the basic blueprint of our solar system: rocky, watery worlds close to their stars and gas giants farther away. But WASP-12b demonstrated that the universe was far more imaginative. A world where diamonds could form naturally, where clouds might consist of graphite dust, where chemistry favored the blackness of soot over the reflection of water vapor. Such a planet redefined the boundaries of what was possible. One particularly captivating theory suggested that WASP-12b's carbon dominance was directly responsible for its extreme darkness. Without the reflective silicate clouds found in more oxygen-rich planets, its atmosphere would have no means of bouncing light back into space. Instead, the carbon compounds would absorb and trap radiation, amplifying both the heat and the darkness. This theory linked two of the planet's defining mysteries, the blackest planet phenomenon and its carbon-rich chemistry, into one elegant, if unsettling, explanation. Spectroscopic studies with the Hubble and Spitzer space telescopes strengthened this hypothesis. By analyzing the planet's emission spectra at different wavelengths, scientists noticed consistent absorption signatures that matched complex carbon molecules. What they didn't see were strong water lines, a sign that oxygen was indeed a minority element. This result wasn't just about one strange world, it was a revelation about how diverse exoplanets could be. The chemistry of WASP-12b proved that planets could form in conditions previously thought impossible, rewriting the rules of cosmic evolution. The broader implications reached deep into the question of life itself. If carbon-rich planets were common, could they host forms of life built on entirely different chemistry? On Earth, carbon and oxygen coexist to create the building blocks of life, sugars, proteins, and lipids. But in a world where oxygen was scarce and carbon dominated, the molecular possibilities would change. Any potential life, if it could exist in such infernal conditions, would operate on alien principles, with structures and metabolisms we can barely imagine. It was an eerie thought, a diamond world with carbon-based life evolving in pitch darkness under a star that was slowly consuming it. However, the possibility of habitability was only a theoretical curiosity here. WASP-12b's proximity to its star ensured that no known form of life could survive. The temperatures exceeded those of molten rock, and the radiation was enough to vaporize molecules before they could assemble. Yet for planetary scientists, the intrigue wasn't about life, it was about origins. How had a world so extreme come to exist in the first place? How had it maintained its fragile orbit without collapsing long ago? And what could it teach us about the outer reaches of possibility in the universe? The more astronomers studied WASP-12b, the clearer it became that the carbon enigma wasn't just a feature, it was a signature of the planet's entire existence. Every mystery seemed to tie back to it: the absence of light, the structure of its atmosphere, the manner of its death. Even the process of being consumed by its star might be influenced by this chemistry, as the dense, carbon-heavy gases interacted differently with stellar winds and radiation. It was as though the planet's very identity, from birth to destruction, was defined by the element that also forms the backbone of life on Earth. WASP-12b mirrors our own world's chemistry, twisted and intensified by proximity to a violent star. The discovery of WASP-12b's carbon-dominated composition didn't just astonish astronomers, it shook the foundations of planetary science. Until that moment, everything scientists understood about how planets form and evolve was built upon one simple assumption: that oxygen, the most abundant element after hydrogen and helium in the universe, is the dominant chemical sculptor of planetary systems. The idea that a planet could flip that balance, becoming carbon-rich instead, challenged every established theory of cosmic chemistry. For decades, astronomers believed that most stars, and by extension their planets, formed from similar proportions of hydrogen, helium, oxygen, carbon, nitrogen, and silicon. That chemical balance shaped the familiar worlds of our solar system: rocky planets with silicate crusts, icy moons with water-rich mantles, and gas giants with atmospheres abundant in hydrogen, helium, and water vapor. Oxygen was the silent architect of this order. It bonded with metals to make rocks, with hydrogen to form water, and with carbon to regulate the chemistry of atmospheres. Then came WASP-12b. Here was a world orbiting its star so closely that it was being devoured. Yet instead of following the oxygen-heavy chemistry seen elsewhere, it seemed to favor carbon. A planet that was essentially built from soot and diamond dust, rather than the water and silicate foundations of Earth or Jupiter. When astronomers realized that its carbon-to-oxygen ratio exceeded 1, it became clear that not all planets are born equal, or even born under the same cosmic rules. This revelation forced scientists to confront an uncomfortable question: what if carbon-rich planets are not rare outliers, but part of a vast, unseen category of worlds scattered throughout the galaxy? If carbon can dominate in one planetary system, it could dominate in others. That possibility rewrote the map of what kind of planets might exist, and what kind of chemistry might define them. The formation of a carbon world begins in the swirling chaos of a protoplanetary disk, the cloud of gas and dust that orbits a newborn star. Normally, oxygen combines with silicon and metals to form silicate minerals, while hydrogen bonds with oxygen to make water. In regions where oxygen is plentiful, you get planets like Earth or Neptune. But in regions where carbon is abundant and oxygen is scarce, a very different chemistry emerges. Carbon atoms bond with silicon to form silicon carbide, with metals to make metallic carbides, and with itself to create graphite and diamond. The result is a world where the familiar rocks of Earth are replaced by alien minerals, hard, dark, and carbon-based. On such a planet, the landscapes would be unimaginably different. Instead of oceans and continents, there might be vast plains of graphite, mountains made of glittering diamond, and clouds of hydrocarbon haze drifting across the sky. Even the weather would operate under strange rules, with methane and acetylene replacing water vapor as the dominant atmospheric gases. Lightning might spark through carbon-rich storms, and rain could fall as droplets of liquid hydrocarbon or even microscopic diamonds, depending on pressure and temperature. This is the world that WASP-12b hinted at. Not just a single bizarre exoplanet, but a new class of worlds, carbon planets. Before its discovery, the concept of carbon planets existed only in theory. In 2005, astronomer Mark Kuchner and astrophysicist Sarah Seeger proposed that planets forming around carbon-rich stars could have entirely different compositions. Their papers described possible diamond planets, graphite worlds, and carbide crusts. At the time, these ideas were speculative, beautiful science fiction more than observational reality. But WASP-12b's spectral data turned that speculation into evidence. It became the first strong indicator that such planets truly exist. The implications were staggering. If carbon worlds were real, they might be more common than anyone had imagined. After all, the Milky Way is filled with stars that vary widely in composition. Some have more carbon relative to oxygen, and some have less. If planetary formation follows local chemistry, then entire systems could be born with carbon-dominated disks. That would mean millions, perhaps billions of such planets scattered across the galaxy, invisible to us now, but waiting to be found. The discovery also reshaped the conversation about how and where planets form. Traditional models assumed that gas giants like Jupiter formed beyond the snow line, the distance from a star where water can condense into ice. But WASP-12b's chemistry didn't fit that template. It either formed in a carbon-rich region much farther out, or its composition was altered after migration inward. Either scenario demanded new thinking. If planets can migrate from one chemical zone to another, then the boundaries of what kinds of planets can exist, and where, are far more flexible than once thought. Scientists began to revisit the idea of carbon worlds elsewhere. Observations of 55 Cancri E, another super-Earth exoplanet located 41 light-years away, revealed signs of high carbon content, leading some to speculate that it might also be a carbon planet. Similarly, the mysterious exoplanet LHS 3844b, with its ultra-dark surface and lack of atmosphere, could represent another variation of this chemistry. These discoveries suggested that WASP-12b was not alone. It was part of a broader family of planets formed under different cosmic conditions. But WASP-12b's significance went beyond cataloguing exotic worlds. It revealed that carbon and oxygen, the twin elements of organic chemistry, could rearrange themselves in ways that completely transform a planet's destiny. On Earth, their delicate balance makes life possible. Too much carbon without enough oxygen, and our world would be suffocating and barren. Too much oxygen without carbon, and the molecules of life could never form. WASP-12b, in contrast, represented the opposite extreme, a world so rich in carbon and so poor in oxygen that it became a mirror image of life's cradle, a dark, fiery reflection of what might have been had our cosmic recipe been different. For astronomers, this discovery brought new urgency to a fundamental question: what makes a planet habitable? If worlds can form with wildly different elemental ratios, then the ingredients for life could vary as much as the planets themselves. The habitable zone, once defined simply by temperature and distance from a star, now seemed too narrow a measure. A carbon planet might have the right temperature, but completely alien chemistry. Could such a world ever support life as we know it? Probably not. But could it host life as we don't know it? That's a harder question to answer. The search for carbon worlds also intersected with another area of research: the study of carbon stars. These are stars in later stages of life that shed carbon into space through stellar winds, enriching the interstellar medium with carbon dust. When new planetary systems form around such stars, that excess carbon becomes the raw material for planets. In this way, carbon worlds may be the children of dying stars, cosmic heirs to ancient stellar forges. That connection between death and creation is echoed in WASP-12b's own fate. Even as it is being consumed by its star, it reveals secrets about the processes that shape worlds across the universe. It's almost symbolic. A dying planet teaching us how planets are born. Its destruction illuminates the diversity of life cycles among celestial bodies. The same forces tearing it apart are helping scientists rebuild the timeline of how carbon and oxygen shape worlds on a cosmic scale. The existence of carbon worlds also carries practical consequences for future exploration. When telescopes like the James Webb Space Telescope and its successors analyze exoplanet atmospheres, they rely on detecting chemical signatures, light absorbed by specific molecules. Understanding carbon-rich chemistry is essential to interpreting those signals correctly. A planet that looks empty in one wavelength might actually be brimming with exotic compounds, invisible under oxygen-based models. By learning from WASP-12b, astronomers refine their tools for detecting and understanding worlds far more alien than we once thought possible. Moreover, the existence of carbon worlds expands the potential for discovery beyond the habitable zone. Traditional searches for Earth-like planets focus on those that might host water, but in a universe where chemistry can take so many paths, habitability might come in different forms. Some scientists have suggested that carbon planets could retain atmospheres longer or resist certain types of radiation damage due to their dense carbon crusts. While such worlds would be inhospitable by human standards, they could still be stable and enduring, surviving long after their oxygen-rich cousins are stripped away. WASP-12b thus became a bridge between the known and the unknown, between the worlds we understand and the ones that defy understanding. Its carbon enigma gave rise to a new field of inquiry, forcing scientists to rewrite textbooks, redesign models, and rethink the way they define planets themselves. It showed that the blueprint of the cosmos is not uniform, but wildly creative. Stars, disks, and planets can mix their ingredients in countless ways, producing results that range from the familiar to the unthinkable. Comparisons, the galaxy's other nightmares. For astronomers, discovering new exoplanets once meant expanding our sense of the possible. Worlds orbiting twin suns, planets with multiple moons, or distant spheres locked in eternal daylight. But in recent years, discoveries have grown darker. The universe has revealed planets so extreme, so violent in their conditions, that they seem to defy nature itself. Worlds of fire, wind, and ice where the laws of physics bend under cosmic strain. Yet even among these horrors, one planet remains singular. WASP-12b, the Death Planet, still holds its place as one of the most terrifying examples of self-destruction in the galaxy. But to understand why WASP-12b is so haunting, it helps to compare it with the other nightmares orbiting alien suns. Worlds that stretch imagination to its limits and make Earth seem impossibly calm. The first among these cosmic infernos is Kelt 9b, a world so hot it nearly merges the line between planet and star. Discovered in 2016, it orbits a blue A-type star, roughly 670 light-years away in the constellation Cygnus. Its daytime temperatures reach a staggering 7,800 degrees Fahrenheit, 4,300 degrees Celsius, hotter than the surface of many stars and twice as hot as molten lava. At such extreme heat, molecules are torn apart into atoms. Hydrogen and iron exist in gaseous forms, floating freely like vaporized metal. Even Jupiter's massive bulk couldn't survive under such conditions. Yet Kelt 9b endures, locked in a deadly embrace with its parent star. What's astonishing about Kelt 9b isn't just its heat, but its proximity to its star. It orbits once every 1.48 Earth days, only slightly longer than WASP-12b's suicidal year. The star's ultraviolet radiation is so intense that the planet's atmosphere is being stripped away at an estimated rate of 10 billion tons per second. Astronomers observing with the Hubble Space Telescope detected a vast cloud of escaping hydrogen enveloping the planet, a ghostly halo marking its slow disintegration. It's a world being cooked and consumed simultaneously, glowing faintly blue in the ultraviolet, like an ember that refuses to die. Kelt 9b represents the farthest extreme of heat, a planet that redefines the upper limits of atmospheric endurance. But unlike WASP-12b, it's not being actively stretched by gravity to the point of destruction. It's a planet melting from radiation, not being shredded by tidal forces. That's what makes WASP-12b different. One is being burned alive, the other torn apart from the inside out. Then there's Kepler-70b, a planet that shouldn't exist at all. Roughly 4,000 light-years away in the constellation Cygnus, Kepler-70b orbits a subdwarf star, the exposed core of what was once a sun-like giant. Billions of years ago, its star expanded into a red giant, swelling outward and engulfing its inner planets. Yet somehow, Kepler-70b survived, orbiting closer to the stellar remnant than Mercury does to our Sun. Its orbital distance is less than 1 million miles, completing a full year in just 5.8 hours. Scientists believe Kepler-70b once orbited farther out, but as the star swelled, it was pulled inward, surviving the fiery engulfment only to emerge scorched and skeletal. Its surface temperature is estimated around 12,000 degrees Fahrenheit, 6,700 degrees Celsius, hotter than many stars. Made almost entirely of metal, it's thought to be the dense remnant of a former gas giant, whose outer layers were stripped away during the star's death throes. What remains is a planetary core, a molten metallic survivor circling the ashes of its sun. Kepler-70b is not a planet in the usual sense. It's a relic, the ghost of a world that should have been destroyed. Its very existence challenges the boundaries of survival. In comparison, WASP-12b is still in the middle of its tragedy. Kepler-70b has already endured its apocalypse and lives in the aftermath, while WASP-12b is experiencing its slow death in real time. The difference between them is the difference between ruin and dying. Another of the galaxy's infamous terrors is HD 189733b, perhaps one of the most visually dramatic planets ever discovered. It lies 64 light-years away in the constellation Vulpecula and is classified as a hot Jupiter, much like WASP-12b. At first glance, it might even appear deceptively familiar, a brilliant sapphire world when viewed through the Hubble Space Telescope. But that deep blue color isn't due to tranquil oceans or an inviting sky. It's the reflection of silicate particles, microscopic shards of glass, suspended in the atmosphere. HD 189733b's winds blow at an astonishing 5,400 miles per hour, strong enough to hurl molten glass sideways across the planet's surface. The temperature differences between its day and night sides create violent jet streams, whipping gases into endless deadly tempests. There is no calm, no surface to stand on, no air to breathe, only storms of glass, searing heat, and winds that would shred anything that dared to enter. The planet is a perfect vision of chaos, a sapphire stormscape frozen in perpetual violence. Yet despite the horror of HD 189733b, it is still more stable than WASP-12b. Its star is not devouring it, and its orbit, while close, remains steady. The storms rage eternally, but the planet itself endures. In that sense, HD 189733b represents nature's fury, while WASP-12b embodies its inevitability, the unavoidable consequence of being too close to a cosmic inferno. These are not the only examples of the universe's extremes. There's Corot 7b, a rocky world so close to its star that its dayside surface is an ocean of molten rock, vaporizing stone into a thin mineral atmosphere. There's Tres 2b, the second darkest planet ever discovered, reflecting less light than coal and nearly rivaling WASP-12b in its blackness. And there's Kepler-13ab, whose gravitational gradients are so powerful that heavy metals condense and fall as titanium rain. Each one reveals another dimension of how violently diverse exoplanets can be. Still, WASP-12b stands apart. What makes it unique isn't just that it's hot or close to its star. There are hotter and there are closer. What sets WASP-12b apart is the combination of all its torments. The gravitational stretching that's physically deforming it, the atmosphere being siphoned away into a swirling accretion disk, the carbon-rich chemistry making it unnaturally black, and the doomed trajectory that ensures its eventual annihilation. It's not merely surviving extremes, it's actively disintegrating. It is a planet in the process of erasing itself. In a universe of violent worlds, WASP-12b is the one that chose self-destruction as its fate. Its orbit is so tight that it crosses the Roche limit, meaning the gravitational pull from its star is stronger than the planet's own ability to hold itself together. This creates tidal forces so immense that the planet is literally being pulled into an elongated egg-like shape. Over time, those forces will tear away its atmosphere, its mantle, and eventually its core. Every orbit brings it closer to the point of no return. Scientists estimate that within 3 to 10 million years, an instant on the cosmic scale, WASP-12b will be gone, its mass completely absorbed by its star. This process is so rare that Hubble's 2010 observation of gas streaming from the planet marked the first time astronomers had ever seen a star visibly consuming a planet. It wasn't just a curiosity, it was a preview of the future. One day, billions of years from now, our own sun will swell into a red giant and consume Mercury, Venus, and possibly Earth. WASP-12b is, in a sense, a mirror of our own solar system's eventual fate. That's what makes it terrifying. Not just its destruction, but the reminder that planetary death is not an anomaly. It's part of the natural cycle. Every world that orbits a star is destined, eventually, to face its end. Some will freeze in the void when their stars die out. Others will burn when their suns expand. And a few, like WASP-12b, will perish in the jaws of their parent stars, giving their final light back to the fire that once gave them life. In studying these cosmic nightmares, Celt-9b, Kepler-70b, HD 189733b, and WASP-12b, astronomers are learning that the universe is both artist and executioner. It paints with radiation, gravity, and chemistry, crafting worlds of impossible beauty and unbearable violence. Every discovery expands our understanding of what it means to be a planet. Once, the word planet conjured images of green hills and blue skies. Now, it includes molten wastelands, diamond deserts, and worlds that rain glass. The diversity of these planets isn't random. It's the result of cosmic evolution at its most creative. A star's temperature, composition, and age shape the destinies of its worlds. A planet's distance determines whether it freezes, burns, or shatters. And chemistry decides its colors, its storms, and its death. The more we study exoplanets, the clearer it becomes that our solar system is not the rule, it's the exception. For every tranquil, life-bearing world like Earth, there are countless others like WASP-12b, tortured, collapsing, and consumed by their suns. The universe, vast and ancient, doesn't promise balance. It offers only variety, from the gentle to the grotesque, from the nurturing to the annihilating. And yet, even in that brutality, there is meaning. Each world tells us something about the extremes of creation. WASP-12b teaches us how far gravity can push a planet before it breaks. Celt-9b shows how temperature can dissolve chemistry itself. Kepler-70b proves that destruction can give birth to survivors. HD 189733b reminds us that even beauty can hide violence. Together, they form a gallery of cosmic extremes, a reflection of a universe that thrives on contrast. The last light, how stars die and rebirth the universe. The death of a planet can seem dramatic, but the death of a star reshapes galaxies. It is the quiet engine of cosmic renewal, an event so catastrophic that it forges the very atoms of life from pure destruction. Every breath we take, every element in our bodies was born in a star that lived, burned, and finally collapsed. Stars are not eternal. They are living processes of energy and gravity, balanced on the edge of collapse. Their lives begin in cold, dense clouds of hydrogen and dust drifting through interstellar space. The birthplace is known as nebulae. Gravity slowly pulls particles together, and as the mass grows, so does the pressure at its core. Once the temperature reaches millions of degrees, hydrogen nuclei begin to fuse into helium, releasing energy in a chain reaction that ignites a new sun. From that moment, the star shines, locked in a delicate equilibrium between the outward push of radiation and the inward pull of gravity. For billions of years, this balance defines the life of a star. The larger the star, the faster it burns its fuel. Smaller stars, like our own Sun, sip their hydrogen slowly, burning for 10 billion years or more. Massive stars, however, live fast and die young, some lasting only a few million years before exhausting their cores. The way a star dies depends entirely on its mass, but in every case, the process transforms the surrounding cosmos. Death for stars is both an ending and a beginning. When a star like the Sun nears its final phase, it swells into a red giant. The fusion reactions in its core begin to falter as hydrogen runs out, and gravity starts to win. The outer layers expand, cooling and glowing with a reddish hue. The Sun, for instance, will one day grow large enough to engulf Mercury and Venus, and possibly the Earth, in its fiery shell. Eventually, its outer layers will drift into space, forming a luminous bubble of gas called a planetary nebula. What remains at the center is a dense, cooling ember known as a white dwarf, a stellar corpse, no larger than Earth but holding the mass of the Sun. It will shine faintly for billions of years before fading into darkness. The death of larger stars, however, unfolds with far more violence. When a massive star runs out of nuclear fuel, the outward pressure that held it stable collapses. Gravity suddenly crushes the core inward, igniting a chain of reactions so explosive that the star rips itself apart in a supernova. For a few brief moments, a dying star can outshine an entire galaxy, releasing more energy than our Sun will produce in its entire lifetime. This moment of utter destruction is also one of creation's most important acts. Within those collapsing layers, new elements are forged: iron, gold, carbon, oxygen, and all the heavier atoms that make up planets, oceans, and living things. These supernova explosions scatter their contents across light years of space. The remnants mix with interstellar gas, seeding future generations of stars and planets. Every rock, every cell, every thought we have exists because somewhere, billions of years ago, a star died. Carl Sagan's famous phrase, "We are made of star stuff," isn't poetry, it's literal truth. The calcium in our bones, the iron in our blood, the silicon in the ground beneath our feet, all of it was once trapped in a stellar core before being hurled into the cosmos. Some stars are so massive that even a supernova isn't enough to stop gravity. When their cores collapse, they form neutron stars, or if the mass is high enough, black holes, the ultimate expression of gravitational power. A neutron star is a sphere barely a dozen miles wide but heavier than the Sun, packed so tightly that a teaspoon of its material would weigh billions of tons. Black holes go even further. They collapse into a point of infinite density, where gravity is so strong that not even light can escape. For years, these objects were purely theoretical, but modern telescopes have now captured their shadows, confirming their existence as the universe's strangest monuments to collapse. Yet even black holes, the most destructive entities we know, play a role in rebirth. As they consume gas and stars, they release enormous amounts of radiation and gravitational energy. This outflow can compress nearby clouds of gas, triggering the formation of new stars. In this way, death becomes a catalyst for life. The galaxy itself is a recycling system. Old stars die, their remnants drift, and from that debris, new stars ignite. It's a cosmic rhythm that has played out for more than 13 billion years, long before Earth existed, and will continue long after it is gone. Our own Sun will not explode in a supernova. It simply doesn't have enough mass, but it will leave behind its own quiet legacy. In roughly 5 billion years, when it expands into a red giant, and sheds its outer layers, those gases will spread into interstellar space. The atoms that once composed our planet could eventually become part of new systems, perhaps forming another world where intelligent beings will look to their sky and wonder who came before them. Astronomers have seen the remnants of such cycles everywhere. The Crab Nebula, for instance, is the ghost of a star that exploded in 1054, recorded by Chinese and Arab astronomers who saw it light up the daytime sky. Even now, nearly 1,000 years later, its colorful tendrils of gas continue to expand outward, glowing with energy from a spinning neutron star at its center. In another corner of the galaxy, the remnants of supernova 1987A are still reshaping the gas clouds around it. Each one is a scar of destruction, but also a womb for new creation. The philosophical implication of all this is profound. In human terms, death is often seen as an ending, the cessation of existence. But in cosmic terms, death is simply transformation. Matter cannot be destroyed, it only changes form. A dying star's light may fade, but its essence continues in new configurations. The same principle governs everything in the universe. Nothing truly ends. WASP-12b, torn apart by its star, will one day become part of that star's own evolution. The star itself will die, scattering new matter into space. The atoms that were once part of that doomed planet might later assemble into another world, orbiting another sun. In the universe, even tragedy recycles. That realization reshapes how astronomers see themselves and their work. When they study dying stars, they aren't just cataloging destruction, they're tracing the lineage of existence. Every element on their instruments, every molecule in their bodies, carries a history billions of years deep. When they measure the spectrum of a supernova or analyze the chemical traces in a distant nebula, they are reading the autobiography of the cosmos itself, one written in light and time instead of words. It's almost paradoxical that something as final as stellar death could be the source of all beginnings. Without it, there would be no complex chemistry, no carbon life, no rocky planets. The universe would remain a featureless sea of hydrogen and helium. Instead, every generation of stars builds upon the ruins of the last. Each explosion enriches the cosmic dust, allowing new worlds to form with more intricate materials. By the time our solar system was born, the galaxy had already experienced many such cycles. The Sun and its planets are the descendants of countless ancient stars, long vanished, but whose remains still live within us. There's a haunting beauty in that continuity. Imagine the universe as an endless ocean, with stars as waves rising and falling over unimaginable spans of time. Each crest shines, breaks, and dissolves, but the ocean remains. The light of dead stars still travels across space, reaching us thousands or millions of years later. Every starlit night, we are surrounded by ghosts, the final light of suns that no longer exist. Their deaths happened long before human history began, but their light is still arriving, telling their stories in silence. For all its enormity, this process connects directly to human experience. We too are temporary arrangements of matter and energy, destined to dissolve and return to the larger system. Our individual lives may be brief, but the atoms that compose us are ancient, born in furnaces older than Earth. When we die, they will scatter again, continuing the cycle. Seen from that perspective, death becomes less of an ending and more of a continuation, a quiet merging with the larger story of the cosmos. The poetic irony is that in a universe filled with destruction, creation never stops. Black holes merge and send ripples of gravity across the void. New stars form from the wreckage of the old. Even galaxies collide and birth new structures in the aftermath. The cosmic clock never pauses. It simply resets endlessly. What we call the end is just another beginning, playing out on a scale far beyond human comprehension. When astronomers gaze at supernova remnants or study the final breaths of red giants, they aren't witnessing tragedy. They're seeing renewal. They're looking at the raw machinery of existence, where energy transforms but never disappears. The last light of a dying star is not a lament, it's a promise. It says that from this fire, something new will come. In this way, the universe offers its own quiet philosophy. Nothing lasts, but nothing is wasted. Every death enriches the next generation of life. Every fading light seeds another dawn. The cosmos does not mourn its endings, it builds upon them. And perhaps, in that endless renewal, there lies a kind of comfort. The universe teaches us that even the most violent destruction has purpose, not by design but by consequence. For those who spend their lives studying the stars, that truth is both humbling and inspiring. To watch the universe die, piece by piece, and know that it will also endlessly recreate itself, is to see beauty in impermanence. The story that began with WASP-12b, a planet being devoured, now widens to encompass everything that is and ever will be. Death, it turns out, is not the darkness swallowing the light. It is the moment before rebirth, the space between endings and beginnings. How the universe recycles itself through cosmic collisions. If the death of a planet like WASP-12b feels like a tragedy, then the story of colliding galaxies is its grand cosmic redemption. The same cataclysmic forces that rip worlds apart also forge the raw ingredients for new stars, planets, and perhaps new beginnings. The universe does not waste. It recycles itself endlessly, turning chaos into order and order back into chaos, in a rhythm that has pulsed for over 13 billion years. When astronomers look into deep space, they don't just see isolated galaxies moving serenely through the void. They witness an intricate ballet where gravity acts as both choreographer and destroyer. Massive galaxies, each home to billions of stars, drift together over billions of years, drawn by their mutual gravitational pull. What happens when they meet is both terrifying and magnificent, a slow-motion collision that reshapes everything within them. Stars are flung across space, gas clouds compress and ignite into bursts of star formation, and entire galactic identities dissolve and reform. It's not an explosion as we imagine it. These collisions play out over hundreds of millions of years, but the results are no less dramatic. Consider the antennae galaxies, one of the most striking examples of two galaxies locked in a cosmic embrace. When the Hubble Space Telescope captured their intertwined arms of stars and glowing gas, astronomers saw not just a scene of destruction, but rebirth. Vast regions within the merging galaxies are bursting with new stars, nurseries ignited by the violent compression of interstellar gas. These newborn stars, massive and short-lived, will soon die in supernova explosions, seeding their surroundings with heavier elements like carbon, oxygen, and iron. Those very elements are the building blocks of planets, oceans, and even life. In this way, the collision becomes a cycle, a vast cosmic act of recycling, where the end of one system becomes the genesis of another. And yet, each galactic collision tells its own story. In some, like the Milky Way and Andromeda, which are destined to collide in roughly 4 billion years, the result will be a new, larger galaxy, what astronomers call Milkomeda. Despite the scale of this event, it's unlikely that our Sun, or any other individual star, will directly crash into another. The distances between stars are too immense. Instead, their orbits will be jostled and reshaped, and the gas and dust that float between them will be stirred up, triggering new waves of star formation. From our vantage point, the night sky will transform over eons as new constellations emerge and the galaxy itself morphs into a new form. Humanity, if still around, would witness a sky unlike anything our ancestors could imagine. But not all mergers are equal. Some are violent, fast, and final. When a small galaxy collides with a larger one, it's often torn apart, its stars stretched into long, shimmering tidal streams. These ghostly ribbons, still visible in many galaxies, are the lingering signatures of such ancient cannibalism. Our Milky Way itself has consumed many smaller galaxies over its lifetime, including the Sagittarius dwarf galaxy, whose remnants can still be traced orbiting us. Each of these consumed systems contributes new stars, gas, and dark matter to the Milky Way's structure, an act of cosmic assimilation that has shaped the galaxy we now call home. From a philosophical perspective, these collisions echo the universe's deeper truth that nothing is ever truly lost. The atoms that once composed ancient stars now flow through our bloodstreams. The dust of shattered worlds drifts in the space between galaxies, waiting to coalesce into something new. Even black holes, the ultimate symbols of annihilation, participate in this grand cycle. When two galaxies merge, so too do their central supermassive black holes, unleashing torrents of energy as they spiral inward and collide. The gravitational waves produced by these titanic events ripple across space-time itself, carrying with them the story of creation's most violent moments. Astronomers have long wondered how such destruction could lead to beauty. The answer lies in physics itself. Energy, matter, and motion cannot vanish, they only transform. When galaxies collide, they release gravitational potential energy, fuel for new stars. The shock waves from the collision compress molecular clouds, sparking the birth of thousands of suns. What appears chaotic on one scale becomes harmonious on another. From entropy emerges structure. From disorder, new beginnings. Modern telescopes like James Webb are now capturing these collisions in unprecedented detail. Through its infrared eyes, Webb can peer through the thick dust that once hid the hearts of merging galaxies, revealing the fiery cradles of newborn stars. In some cases, it shows black holes feasting on torrents of gas, lighting up the universe as quasars, so bright they outshine entire galaxies. In others, Webb reveals quiet mergers, where star formation has slowed, leaving behind elegant elliptical galaxies that shine softly in the dark, like cosmic embers cooling after a storm. Each of these snapshots adds another verse to the universe's ongoing poem of renewal. It reminds us that the cosmos does not operate in static perfection, but in perpetual evolution. The collisions we observe today are not accidents but inevitabilities. Gravity ensures that galaxies will find each other, merge and transform. The universe, expanding though it may be, is also deeply interconnected, every interaction rippling outward, shaping the fate of countless systems we will never see. Beyond the scientific marvel lies a deeply human resonance. Watching galaxies collide is like watching time itself sculpt the heavens. It's a reminder that endings are not always tragedies. Sometimes they're transitions. Just as stars are born from the ashes of older generations, entire galaxies are forged from the remnants of others. We too are part of this continuum. The iron in our blood was once fused in the core of a massive star that exploded billions of years ago. The calcium in our bones, the oxygen we breathe, even the carbon that forms the backbone of life, all are cosmic hand-me-downs from the universe's long history of collision and renewal. This endless cycle challenges how we think about permanence. Nothing in the cosmos stays the same, not even the stars. Galaxies merge and fade, stars are born and die, and planets are devoured or remade. Yet through all this impermanence, there is continuity. The universe endures because it changes. Every death gives rise to new forms. Every collision plants the seeds of future creation. In that sense, the cosmos mirrors life, fragile, dynamic, and unceasingly creative. The galaxies we see colliding today are so far away that their light began its journey long before life arose on Earth. By the time their story reaches our telescopes, their destinies may already have changed. And yet, even from this distance, we can recognize something profoundly familiar in their turmoil, a reflection of the cycles that define existence itself. In a universe defined by movement, destruction is never final. Every collision, every explosion, every slow dissolution of a dying world feeds into the next act of creation. The echoes of these events stretch across billions of years, reverberating through the very matter that composes everything we know. It's a cosmic truth, both humbling and beautiful, that even in its most violent moments, the universe is never at war with itself. It is simply becoming. How the universe reflects its own past. The universe, for all its immeasurable size and mystery, is also a storyteller. Every particle of light that moves through its vastness carries a memory, a fragment of what once was. When we look into the night sky, we're not seeing the present at all. We're seeing the past written in light. The stars above us are not distant fires burning now, but ancient signals, crossing oceans of space and time to reach our eyes. This simple truth, that light takes time to travel, turns the entire cosmos into a living archive, a mirror reflecting its own history across billions of years. Every time we gaze through a telescope, we are time travelers. The light from our sun takes 8 minutes to reach us, meaning we always see it as it was 8 minutes ago. The light from the nearest star, Proxima Centauri, left 4 years ago. The light from the Andromeda Galaxy, the Milky Way's massive neighbor, began its journey more than 2.5 million years ago, when early humans were still shaping stones into tools. And when we peer deeper, beyond the galaxies, into the faint background glow that fills the universe, we're looking at light that has been traveling for nearly 13.8 billion years, radiation left over from the Big Bang itself. This cosmic mirror stretches farther than our imagination can grasp. Each point of light we observe in the night sky is a message from a different era. Some stars we see no longer exist. They may have exploded long ago, their light still crossing the void, carrying their final farewell. Others are so young that their first rays are only now arriving on Earth. The universe, in this sense, is not a static stage, but a living history book still being written. The concept of look-back time is one of the most poetic ideas in astrophysics. It describes how the farther we look into space, the further back we see in time. This isn't a metaphor, it's literal. Because light travels at a finite speed, about 186,000 miles per second, even a beam from the most distant galaxy must cross unimaginable distances before reaching us. That means our telescopes don't just capture what is, but what was. In every direction, the cosmos shows us its earlier versions, as if each layer of distance were a layer of memory. The James Webb Space Telescope, JWST, launched to peer deeper into the infrared universe, has become humanity's most powerful time machine. Its golden mirrors capture faint light from the first galaxies that ever formed, structures that existed just a few 100 million years after the Big Bang. When astronomers process these images, they're not merely looking at old starlight. They're witnessing the moment when the first atoms of hydrogen gathered under gravity's pull to ignite the universe's first suns. Each new discovery Webb makes rewrites the story of our cosmic dawn, challenging everything we thought we knew about how galaxies were born. Yet the infinite mirror of the universe doesn't only reflect distance, it reflects transformation. When scientists observe galaxies billions of light years away, they see young, chaotic systems bursting with star formation and tangled streams of gas. Closer galaxies, by contrast, appear older, calmer, more structured. This isn't just coincidence, it's a timeline. The farther we look, the younger the universe appears. The closer we look, the more mature it becomes. By studying galaxies at different distances, astronomers can piece together the stages of cosmic evolution, like flipping through a photo album that begins at creation and ends with the present. The cosmic microwave background is the oldest light we can possibly detect, the faint afterglow of the Big Bang. It's everywhere, bathing the entire universe in a nearly uniform field of radiation. But within that uniformity lie subtle ripples, variations in temperature and density so slight that they differ by less than 1 part in 100,000. These ripples are the fingerprints of the universe's birth, the first seeds from which galaxies, stars, and planets would eventually grow. When scientists map the CMB, they are essentially staring at a baby picture of the universe, a portrait of existence when it was only 380,000 years old. What's extraordinary about this cosmic reflection is that it doesn't fade. Light, unlike sound or scent, doesn't dissipate easily. It can travel through the vacuum of space indefinitely unless absorbed or scattered. This means that the universe preserves its own memories in the form of photons, the particles of light that stream endlessly through the cosmos. A single photon emitted by a star billions of years ago can still, in theory, be detected today. The universe, therefore, never truly forgets. It remembers everything that has ever shone. But this reflection is also selective. Some light never reaches us. Dust clouds, dark matter, and the expansion of space itself can distort or obscure what we see. Galaxies moving away from us stretch their light into longer wavelengths, a phenomenon known as redshift. The greater the redshift, the faster the galaxy is receding, and the older the light we're seeing. This cosmic stretching is like the universe's own clock, one that tells us how quickly it's expanding and how long ago the light began its journey. With this knowledge, astronomers can measure not only distance, but also the universe's age, revealing how the cosmos has evolved from a dense, hot plasma into a vast web of galaxies spanning the infinite dark. But what does it mean that the universe can reflect its own past, yet we can never see its present? Every observation we make is an echo, a delayed message from epochs long gone. The cosmos we observe no longer exists in the form we see it. In essence, we are constantly looking at ghosts, luminous relics of moments that no longer are. And yet, in a strange way, this gives the universe a kind of consciousness, not in the human sense, but in a structural one. Its very nature is memory. Every interaction, every collision, every burst of starlight is recorded in the endless traffic of photons. To study the universe, then, is to study memory itself on the grandest possible scale. The atoms in our bodies are part of that memory too, forged in ancient stars whose deaths sent their ashes into space. We are not just observers of cosmic history, we are participants in it. We carry its story within us. Even black holes, once thought to erase information, may contribute to this infinite reflection. Stephen Hawking proposed that black holes emit radiation and may eventually release the information they consume in an altered form. If true, it would mean that not even the most powerful forces in the universe can destroy its memories completely. Instead, they transform them, just as everything else in the cosmos does. Modern cosmology has become an exercise in decoding these reflections. Each wavelength of light tells a different story. Visible light shows us stars. Infrared reveals heat and dust. X-rays expose violent collisions, and radio waves map the invisible structure of galaxies. Together, these layers create a multi-dimensional reflection, a cosmic mirror that doesn't just show what happened, but how it happened. By reading these signals, scientists reconstruct the universe's biography from the instant of its birth to its possible futures. In a profound sense, the universe's reflection is also humanity's mirror. Our curiosity, our drive to understand where we came from, mirrors the cosmos's own self-revelation through light. When we build telescopes, we are extending our senses into the past, pulling the memories of creation closer. Each discovery, each faint glimmer from a distant galaxy, deepens our understanding not just of the universe, but of ourselves. We learn that we are not apart from the cosmos, but expressions of it, temporary configurations of the same energy and matter that have cycled through eons of cosmic history. The next generation of telescopes will look even farther, even deeper, possibly glimpsing the moment when the first stars flickered to life after the cosmic dark ages. And beyond that, new theories may help us see through the distortions of dark matter and dark energy, revealing what lies beyond the horizon of our current understanding. The universe will continue to expand, its galaxies drifting farther apart, their light stretching into longer and longer wavelengths. One day, trillions of years from now, distant observers, if any remain, may find the sky almost empty, the ancient light faded into invisibility. Yet even then, those photons will still exist, still carrying the memory of everything that ever was. The final transmission, when stars speak through light. When a star approaches the end of its life, its light begins to change. Subtly at first, then dramatically. Its color shifts, its brightness fluctuates, its spectrum twists in ways that reveal the violence happening within. To the human eye, this transformation might look serene, a softening glow, a gradual dimming, But through a spectroscope, the story is anything but peaceful. What appears as light is actually a cascade of atomic screams, each wavelength corresponding to the breakdown of stability deep within the star's core. For astronomers, decoding these signals is like reading a last confession. The star tells them everything: what elements it's fusing, how quickly it's burning its fuel, what pressures are building inside. A hydrogen-burning star like our Sun emits a clean, steady spectrum, its light dominated by hydrogen and helium lines. But as the star ages and begins to fuse heavier elements, those lines shift. Carbon, oxygen, neon, and eventually iron start to appear in the light, signatures of nuclear alchemy nearing exhaustion. When those iron lines emerge, scientists know the end is near. In its final centuries, or sometimes mere days, a dying star begins to pulse. Its energy becomes unstable, flowing in waves that push its outer layers outward. These pulsations send rhythmic changes through its light, like a heartbeat slowing to a stop. Each oscillation carries precise information about the star's internal structure, its density, temperature, and even the rhythm of its nuclear reactions. The study of these vibrations, known as asteroseismology, allows astronomers to listen quite literally to the music of dying stars. The data reveals harmonies of matter and energy that play for eons, long after the star itself has gone dark. Some stars end their lives quietly, slipping into obscurity as white dwarfs, dense remnants no larger than Earth, but packed with the mass of the Sun. These stellar corpses no longer fuse elements, but they still emit faint light, thermal radiation that slowly cools over billions of years. That light, though fading, is still a kind of message. It tells astronomers exactly how long the remnant has been cooling, allowing them to date the age of entire star clusters. Even in death, the star continues to mark time, serving as a cosmic clock that never truly stops ticking. Other stars die far more dramatically, in supernova explosions so powerful they briefly outshine entire galaxies. When a massive star runs out of nuclear fuel, gravity crushes its core until it collapses, rebounding in an explosion that tears it apart. The light from that event, the final transmission, can travel across the universe, carrying the star's death cry for millions of years. In those few seconds of destruction, elements heavier than iron are forged in the shockwave: gold, platinum, uranium, and other building blocks of planets and life. Every atom of gold on Earth once flashed through a dying star's explosion, sent hurtling across the cosmos in its radiant farewell. The spectrum of a supernova is like a forensic record of that cataclysm. By studying its light, astronomers can determine not only what type of star exploded, but also how far away it was and how fast its remains are expanding. Even centuries later, the light echo from the explosion can still bounce off interstellar dust, reappearing in space like a ghostly replay of the original event. These light echoes allow scientists to witness supernova that occurred hundreds or even thousands of years ago, as though the universe were replaying its own history. But not all transmissions are violent. Some are slow, melancholic endings, like red giants quietly shedding their outer layers into space. As they do, they create ethereal structures known as planetary nebulae, glowing clouds of gas that radiate in ultraviolet and visible light. To telescopes, these nebulae appear as colorful rings or bubbles, floating in the void like cosmic lanterns. They are, in truth, the star's dying breath made visible, its last exhalation of energy before collapsing into a white dwarf. The light from these nebulae can linger for tens of thousands of years, long after the star's core has gone silent. And then there are the stars that die into darkness, collapsing into neutron stars or black holes, where the final transmission takes on a different form entirely. Neutron stars, only a few miles wide, emit intense beams of radio waves as they spin, becoming pulsars. Each pulse is a rotation, a steady beat that can last for millions of years. These pulses are so precise that they rival atomic clocks, marking time across the galaxy with cosmic accuracy. When astronomers tune into them, they are listening to the heartbeat of collapsed suns. the remnants of explosions still speaking through radio frequencies long after their light has gone out. Black holes, meanwhile, are often thought of as silent, the ultimate erasers of light. Yet even they may have a kind of transmission. As matter spirals toward a black hole's event horizon, it heats up to billions of degrees, releasing torrents of X-rays and gamma rays before disappearing forever. This radiation, captured by observatories like Chandra and NuStar, becomes the black hole's final message, the last signal from infalling matter before it crosses the threshold into oblivion. In a way, black holes are the universe's punctuation marks, ending sentences of light with a silence so complete that only gravity remains. The final transmission of a star doesn't just tell us about death, it tells us about transformation. Every photon released carries information about what came before. The heavy elements born in the star's core are expelled into interstellar space, where they mix with gas and dust, forming new generations of stars and planets. The same light that signals an ending also illuminates the path to new beginnings. Through this endless cycle, the universe becomes its own storyteller, passing knowledge from one generation of stars to the next. Astronomers often describe this in poetic terms. They say that when they study the light from distant stars, they are reading the letters of creation. Each spectral line is a symbol, each pulse a word, each flare a sentence written in the language of physics. Together, these transmissions form an unbroken dialogue that stretches from the dawn of time to the farthest reaches of the cosmos. We are, in a very literal sense, eavesdropping on eternity. Even the faintest remnants of these transmissions matter. When a supernova's light fades and its debris disperses, its particles drift through space, colliding with others, sparking new chemical reactions. Some of those particles eventually find their way into the molecular clouds that birth new solar systems. Our own Sun and Earth were forged from such debris, the ashes of long-dead stars. That means the light that once carried their final transmissions still shines, indirectly, through us. Every breath we take contains atoms that once pulsed with stellar energy, every heartbeat powered by the same forces that ignite suns. From this perspective, the final transmission is not a farewell, but a transformation of communication itself. The language of light becomes the language of matter. The star stops shining, but its essence continues to speak through the very elements that compose new worlds. The gold in a wedding ring, the iron in our blood, the calcium in our bones. All of it was once part of a star's final message. For the scientists who dedicate their lives to studying these signals, there is an almost spiritual quality to the work. They sit behind telescopes, collecting photons that began their journey millions or billions of years ago, light that has crossed time itself to reach their instruments. When they decode that light, they are not just analyzing data. They are listening to the universe whisper across epochs, decoding its dying words and discovering that even in death it continues to create. And perhaps that is the true miracle of the cosmos, that every ending is also a message, every silence a transition. The stars that die send their transmissions into the fabric of space, and through that light, we come to understand the great continuity that binds everything together. The universe doesn't mourn its dead. It learns from them. It listens to their final words and uses them to compose the next verse of its infinite song. The stars do not fade quietly. They speak through radiation, through particles, through the echoes of explosions that ripple through galaxies. Their transmissions never truly stop. They simply change medium, moving from light to dust to life. In that sense, every one of us, every planet, every cell, every thought, is part of the ongoing conversation that began with the first light of creation. We are, quite literally, made from the final transmissions of the stars that came before us. The quantum fabric, where reality unravels and rewrites itself. When astronomers gaze into the cosmos, they don't just see stars. They see equations made real, geometry woven with energy, probability shaped into form. Every particle, every flicker of light, every distant world like WASP-12b is a vibration in this grand unseen tapestry. The universe is not built of matter as much as it is built of relationships, connections that persist across impossible distances, linking everything to everything else. To understand this fabric, we must first step beyond what the eye can see. Space, as we know it, is not empty. It is a restless ocean, rippling with invisible waves of possibility. Quantum fields shimmer beneath the surface of reality, each one a boundless sea of energy. From these fields, particles are born and vanish again, flickering like fireflies in the void. The fabric isn't static, it breathes. It is alive with uncertainty. In this realm, cause and effect blur. A photon emitted by a dying star billions of years ago may still whisper to another particle halfway across the universe. Through a strange and delicate phenomenon known as entanglement, two particles can share the same fate, no matter the distance between them. Measure one, and you affect the other instantly, as if the cosmos itself refuses to let them forget they were once united. Einstein called it spooky action at a distance. But what he called spooky, the quantum world calls truth. Reality, it seems, isn't local. The universe doesn't play by the rules of separation. It is a single entity, experiencing itself from countless perspectives. When the first atoms formed after the Big Bang, the quantum field that gave birth to them didn't vanish. It evolved. It remembers. It holds within it the fingerprints of everything that ever was. Just as light from ancient galaxies carries the story of the early universe, the quantum fabric carries its memory. Every interaction, every star that ignited, every planet that died, leaves a faint impression on this cosmic web. This means that somewhere in that trembling fabric, the death of WASP-12b is already written. The moment its atmosphere began to bleed into its parent star, became part of the universal script. The light it gave off during its destruction continues to travel outward, forever carrying the record of that ending. And when it finally reaches us, through telescopes and sensors, we are, in a sense, touching the memory of that world through the fabric of reality itself. What makes this fabric extraordinary is not just its vastness, but its dual nature. It is both fragile and infinite. On one hand, quantum mechanics reveals a universe that is inherently uncertain, a place where position, momentum, even existence itself is governed by probability. On the other, this uncertainty gives rise to everything that is. Its chaos birthing order, noise sculpting meaning. Some physicists suggest that the universe might be a quantum computer, a vast engine that processes information rather than matter. Every particle, every interaction, every collapse of a wave function could be the universe calculating itself. In this view, stars, planets, and even consciousness are emergent results of the cosmos performing its own computation. And then comes the deeper, more haunting possibility, the holographic principle. According to this radical idea, everything we experience in 3 dimensions may actually be a projection from a distant, 2-dimensional surface. Like a cosmic hologram, the information that defines our reality could be encoded on the outer boundary of the universe. Every thought, every atom, every burst of starlight might simply be a shadow cast from that hidden dimension. If this is true, then WASP-12b's death isn't truly an ending. Its data, its heat, its orbit, its light, remain inscribed on the cosmic horizon. It still exists, in a sense, as information. The star that consumed it did not erase it. It merely transformed it. The universe doesn't delete. It recycles through the quantum memory that underlies all existence. In laboratories on Earth, scientists attempt to glimpse this mystery in microcosm. They entangle photons, cool atoms to near absolute zero, and watch as they behave like echoes of the universe's first moments. What they find is always the same. Beneath every solid thing lies vibration. Beneath every rule lies uncertainty. Beneath every end lies continuation. Quantum physics shows that emptiness is an illusion. Even the most desolate corner of interstellar space seethes with virtual particles appearing and disappearing in trillionths of a second. Nothingness, it seems, is never truly nothing. It's potential waiting to become real. And perhaps that's the most poetic truth of all, that even in cosmic decay there is renewal. The death of one planet, the collapse of one star, the silence after one light goes out, these are not losses, but transitions. They feed the fabric. They reinforce the network of connections that gives the universe its depth. Destruction, in this view, isn't the opposite of creation, it's its continuation. Astronomers looking at WASP-12b's spectral data aren't just watching a planet being devoured. They're watching the fabric stretch, twist, and rewrite itself in real time. The light curves, the ultraviolet flares, the temperature shifts. All are signals encoded into the quantum memory of space. To them, it's as if the universe itself is documenting its own story through physics. The deeper they look, the more it becomes clear. Everything that has ever existed still exists, somewhere within the weave. Perhaps not in the way we think, not as matter, not as form, but as resonance, as the faint shimmer of information that refuses to die. This is why, when we look into the night sky, we're not merely seeing the past, we are participating in it. Every photon that touches our eyes began its journey long before our species existed. It carries the memory of places that may no longer be there. And yet, in observing them, we give them life again, collapsing the probabilities of their existence into reality once more. At the edge of quantum theory lies a question that blurs science and philosophy. If observation shapes reality, then what happens when the universe observes itself? Is consciousness a byproduct of physics? Or is physics the result of consciousness becoming aware? Some physicists quietly entertain this idea, that awareness may be woven into the very foundation of the cosmos, that the fabric itself might be awake. The thought is unsettling, yet strangely comforting. Because if the universe is aware, if it truly knows itself, then every loss, every implosion, every vanished world still has meaning. It becomes part of the grand feedback loop of creation. Energy never dies, and perhaps neither does purpose. And so, the story of WASP-12b, the death planet, doesn't end with its disintegration. It continues subtly, invisibly, in the quantum heartbeat of the universe. The star that consumed it flares with new energy. The gas that once formed its clouds now fuels another cycle of light. Somewhere in another region of space-time, that light may strike a cloud of dust, seeding a new world. The fabric folds, unfolds, and begins again. Maybe that's the final truth hidden in the equations, that every end is a rephrasing, not a silence. Every collapse is an echo that sets the next verse of the cosmic song in motion. The quantum fabric doesn't mourn, it weaves. It takes what was torn and makes something new. And through it all, from the birth of the first atoms to the last dying planet, the universe whispers the same secret. Nothing ever truly disappears. It only changes its form, drifts through probability, and waits to be seen again.